Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the ancient world where insects grew as large as hunting dogs, when Earth's very breath was different, and when the rules of life followed patterns we can barely imagine today. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 360 million years ago, the air itself breathes differently. Oxygen molecules drift through an atmosphere that holds nearly twice the concentration found in modern skies, creating a gaseous abundance that flows like invisible rivers through forests that stretch beyond every horizon. Each breath in this ancient world draws in a richness that will never again grace this planet. An atmospheric composition so fundamentally different that it transforms the very possibilities of what life can become. The chemistry of this enriched atmosphere operates according to principles that seem almost fantastical to scientists studying the geological record. Oxygen concentrations reach 35% of total atmospheric volume, compared to the 21% that constrains modern ecosystems. This seemingly modest numerical difference creates cascading effects throughout every biological system, enabling metabolic processes that operate at intensities impossible under contemporary conditions. The continents move slowly toward their great convergence, carrying their cargo of swampland and endless green across oceanic distances. What will become Pangea still fragments across the globe in scattered pieces. But already the landmasses drift closer with the patient inevitability of geological time. Equatorial regions pulse with warmth and humidity, creating greenhouse conditions that nurture growth on scales both intimate and vast. These continental arrangements create climate patterns fundamentally different from those that will characterize later geological periods. The absence of polar ice caps means that temperature gradients between equatorial and polar regions remain gentle, allowing tropical conditions to extend almost to the planet's extremities. Ocean currents flow in patterns that distribute heat more evenly across the globe, creating stable environmental conditions that persist for millions of years. Tree ferns unfurl fronds the size of modern pine trees, their delicate pinnate leaves catching filtered sunlight in patterns that create cathedral-like spaces beneath the canopy. Their trunks, thick and fibrous, lack the woody strength that evolution has not yet perfected, relying instead on internal pressure and the support of neighboring giants to maintain their towering heights. The result is a forest architecture unlike anything in the modern world, where structural interdependence creates communities of mutual support. These ancient trees represent evolutionary experiments in vertical growth that push the limits of non-woody plant architecture. The trunks consist primarily of soft tissues, supported by high internal water pressure, a strategy that works well in the humid, windless conditions of Carboniferous forests. The canopy they create filters sunlight into golden green streams that illuminate a world where photosynthesis works over time to convert atmospheric carbon into living tissue. These forests exist in a state of perpetual drowning and resurrection, following seasonal cycles that wash nutrients across vast distances. Seasonal floods wash across the low-lying landscapes with the reliability of tides, bringing minerals dissolved from distant highlands and carrying away the accumulated debris of growth and decay. When waters recede, new growth emerges from the saturated soil with an urgency that modern ecosystems rarely display. Every square meter of forest floor pulses with competitive energy. Yet the abundance of resources allows for a kind of biological generosity that permits experiments in size, in form, in the very limits of what living tissue can become. The combination of stable climate, abundant moisture, And rich atmospheric chemistry creates conditions where the normal constraints on biological growth relax their grip. Scientists puzzle over the exact mechanisms that created this oxygen-rich atmosphere, working with evidence preserved in ancient rocks and the chemical signatures of long-buried organic matter. The burial of organic matter in vast wetlands certainly plays a central role. Carbon that might otherwise return to the air as carbon dioxide instead becomes locked in accumulating layers of what will eventually transform into coal seams that power industrial civilizations millions of centuries in the future. The process of carbon burial operates on scales that dwarf modern carbon cycling. Vast forests grow, die, and become buried in anaerobic sediments before bacterial decomposition can return their carbon to the atmosphere. This represents one of the largest transfers of carbon from the atmospheric reservoir to geological storage in Earth's history, a process that simultaneously enriches the air with oxygen while removing carbon dioxide. Yet the precise balance of atmospheric chemistry, the delicate interplay between plant evolution, bacterial decomposition, and geological processes remains beautifully uncertain, like a planetary equation with variables that shift across millions of years. Climate models attempting to recreate Carboniferous conditions struggle with the complexity of feedbacks between biological and geological systems. The chemistry of this ancient air follows pathways that modern atmospheric scientists can only model through complex computational simulations. Oxygen concentrations reach levels that would create fire hazards in today's world. Yet the Carboniferous landscape manages this abundance with geological calm. Plants photosynthesize with unprecedented vigor, their metabolisms accelerated by atmospheric conditions that turn every leaf into a more efficient solar collector. The boundary between air and water blurs in the humid atmosphere, creating conditions where moisture hangs suspended like a planetary exhale. Fog and mist become permanent features of the landscape, creating microclimates where humidity approaches saturation levels. These conditions favor organisms adapted to high moisture environments while creating challenges for those dependent on drier conditions. Only took 300 million years for oxygen levels to double from their early atmospheric concentrations. Only took another 100 million for them to begin their slow decline toward modern levels. Only took the span of deep time for Earth to create conditions that would foster the largest terrestrial arthropods in the planet's history. And then, with geological patience, take those conditions away again. Deep beneath the surface, tectonic forces continue their slow-motion dance, creating the geological foundation upon which the Carboniferous biological drama unfolds. The ocean floors spread and subduct with mathematical precision, recycling crustal material in cycles that span hundreds of millions of years. Volcanic outgassing contributes essential gases to atmospheric chemistry, while weathering of newly exposed rocks provides mineral nutrients that flow through river systems into the waiting swamps. The physics of gas exchange in this enriched atmosphere follows principles that seem almost magical to scientists studying fossilized remains in later eras. Arthropod respiratory systems, originally evolved for efficiency in lower oxygen environments, suddenly find themselves operating in conditions of unprecedented abundance. Tracheal networks that once strained to deliver adequate oxygen to active tissues now carry surplus, enabling metabolisms that support larger bodies and more elaborate behaviors. This oxygen abundance creates a world where the fundamental constraints that govern modern life have been temporarily suspended by planetary chemistry. The relationship between surface area and volume, that mathematical reality that keeps most terrestrial arthropods small, encounters atmospheric conditions that shift the equation toward possibilities that evolution will explore with patient thoroughness. Evolutionary pressures that normally favor compact, efficient forms instead reward bold experiments in scale and ambition. The morning light, such as it was in those distant days, filters through an atmosphere that would intoxicate modern lungs. It carries the promise of giants walking among the ferns, of wings that cast shadows larger than eagles, of a world where the very air conspires to grow things beyond the limits that constrain today's smaller, more careful creatures. Each photon that penetrates the canopy illuminates a landscape where size follows different rules. The silence between the sounds of this ancient world carries its own weight and meaning. No bird calls punctuate the humid air, for birds have not yet evolved from their reptilian ancestors. No mammalian rustling disturbs the undergrowth, for mammals remain tiny, marginal creatures hiding in the shadows of larger dynasties. Instead, the soundscape belongs entirely to arthropods and their invertebrate companions, to the whisper of giant wings through oxygen-rich air, to the careful footfalls of segmented legs across forest floors. In this absence of familiar sounds, the Carboniferous world achieves a kind of alien serenity. It is Earth, certainly, the same planet that spins through space today, yet it breathes with different rhythms, dreams with different possibilities, grows toward different limits under the patient watch of the same ancient sun that will continue shining long after these giants have become compressed impressions in stone. Somewhere in the humid distances, something stirs, something large, something that breathes this ancient air and finds it exactly, perfectly suited to the ambitious scale of its existence. The stage has been set by atmospheric chemistry and geological patience. The players are about to make their entrance into deep time's most extravagant experiment in arthropod ambition. The compound eyes detect movement from 30 meters away. Meganeura libelluloides adjusts its flight path with mechanical precision, each of its four wings beating independently through air so rich with oxygen that even its enormous body finds effortless lift. The wingspan stretches 75 centimeters from tip to tip, casting a shadow across the forest floor that would dwarf any modern bird of prey. This is not a bird, though, a bird. This is an insect, grown large in a world that permits such biological audacity. Each wing membrane catches sunlight filtering through the canopy, creating brief flashes of translucent amber as the giant dragonfly navigates between tree trunks that tower like pillars in some vast, living cathedral. The wings themselves represent engineering marvels that evolution will never again achieve on such a scale. Thousands of microscopic cells form the transparent flight surfaces, reinforced by a network of veins that branch and rebranch with fractal complexity. The material is lighter than any synthetic polymer, yet maintains structural integrity under aerodynamic stresses that would tear apart smaller, more delicate wings. The membrane structure reveals itself under close examination as a masterpiece of biological architecture. Each wing consists of a double-layered cuticle separated by hemolymph channels that provide both structural support and a circulatory network for maintaining wing health during flight. The leading edges contain specialized cells that sense air pressure changes, allowing real-time adjustments to wing angle and curvature. Microscopic hairs along the wing surfaces detect turbulence and provide feedback to the thoracic flight muscles, enabling the kind of precision control that permits navigation through dense forest environments. Flight mechanics in this oxygen-rich atmosphere follow principles that seem to defy the limitations later imposed on insect aviation. The thoracic muscles powering those wings operate at metabolic intensities that would be impossible in modern atmospheric conditions. Each contraction draws upon oxygen reserves delivered through tracheal systems that branch like miniature rivers throughout the body, carrying dissolved gases directly to working tissues without the intermediate step of hemolymph circulation that constrains the size of contemporary arthropods. The respiratory system itself represents an evolutionary compromise between efficiency and scale. Spiracles along the thorax and abdomen open and close in rhythmic patterns that regulate airflow through the internal tracheal network. In smaller modern insects, this system works through simple diffusion. But in Meganeura, specialized muscles assist gas movement through the larger distances required to serve peripheral tissues. The result is a breathing apparatus that operates more like a primitive lung system than the passive gas exchange typical of contemporary arthropods. Scientists studying fossilized Meganeura remains puzzled over the precise aerodynamics of such massive insect flight. Wind tunnel experiments using scaled models suggest that the flight patterns required subtle adjustments to wing beat frequency and angle of attack that push the limits of neural coordination. Yet somehow, in the humid skies of the Carboniferous, these giants mastered three-dimensional navigation through forest environments that demanded split-second responses to obstacles and opportunities. The neurological architecture supporting such complex flight control represents one of the most sophisticated information processing systems in the arthropod lineage. The brain, though built on the same basic segmented plan as smaller relatives, contains specialized regions dedicated entirely to visual processing and flight coordination. Neural pathways connecting compound eyes to wing control centers operate with latencies measured in milliseconds, enabling reflexive responses to environmental changes that occur faster than conscious decision-making processes. The hunting strategy unfolds with patient precision. Unlike modern dragonflies that rely primarily on speed and agility to capture smaller prey, Meganeura employs a more deliberate approach suited to its substantial size. It patrols established territories along forest clearings and stream margins, using its elevated vantage point to survey the ground for movement that indicates potential meals. The compound eyes, each composed of thousands of individual photoreceptive units, process visual information with computational power that rivals modern electronic systems. Each ommatidium in the compound eye system contains photoreceptor cells tuned to different wavelengths of light, creating a visual system capable of detecting polarized light patterns, ultraviolet reflections, and minute changes in movement across the visual field. The processing power required to integrate information from thousands of these optical units approaches the computational limits possible with arthropod neural architecture. Yet Meganeura manages this integration seamlessly during high-speed flight through complex three-dimensional environments. Only took 50 million years for dragonfly ancestors to evolve from small aquatic forms into these aerial giants. Only took another 100 million years for atmospheric changes to make such size impossible again. Only took the patient work of deep time to create and then constrain one of the most magnificent flying machines in evolutionary history. Prey detection relies on movement rather than size or species identification. Anything that moves within the visual field becomes a target for investigation. From smaller dragonfly relatives to early amphibians venturing away from water sources, the hunting success rate remains modest by modern predatory standards. But in an environment where prey abundance compensates for the energy costs of maintaining such a large body, modest efficiency proves sufficient for survival and reproduction. The capture mechanism involves precise aerial intercepts that require complex calculations of trajectory, speed, and timing. Meganeura must account for its own momentum, the movement patterns of prey, and environmental factors like wind currents and obstacles when executing hunting maneuvers. The margin for error decreases significantly with body size, as larger organisms possess greater inertia and require more time and space to change direction during flight. Mating displays occur in aerial theaters that stretch across kilometers of forest canopy. Males establish territories over prime habitat and engage in aerial contests that combine elements of combat and courtship. The sound of their wings beating through the humid air creates a rhythmic thrumming that carries across considerable distances, serving as both a territorial advertisement and a mating call that attracts females ready for reproduction. Territorial boundaries follow invisible maps written in chemical signals and behavioral patterns. Males patrol regular routes through three-dimensional airspace, marking key perching sites with pheromone deposits and engaging in ritualized flights that demonstrate fitness to potential mates and warn competing males. These territorial displays require enormous energy expenditures, limiting the number of males capable of maintaining prime breeding locations. The reproductive cycle ties Meganeura populations to aquatic environments, just as it does for modern dragonflies. Females deposit eggs in shallow waters where developing nymphs will spend years growing through successive molts before emerging as winged adults. These aquatic juveniles, themselves impressive predators in their freshwater habitats, represent intermediate stages in a life cycle that spans multiple years and bridges terrestrial and aquatic ecosystems. Fossil preservation of Meganeura specimens occurs primarily in fine-grained sediments deposited in quiet water environments. The delicate wing membranes rarely survive the fossilization process intact, leaving paleontologists to reconstruct flight capabilities from fragmentary remains and comparative studies of related species. Complete specimens, when they occur, provide invaluable insights into body proportions and wing architecture that inform understanding of Carboniferous atmospheric conditions. The ecological role of these giant dragonflies extends beyond simple predation. As apex aerial predators in their forest environments, they exert selective pressure on prey populations that shapes evolutionary trajectories for multiple lineages of smaller arthropods. Their presence creates behavioral modifications in prey species, influencing activity patterns, habitat preferences, and anti-predator adaptations that cascade through entire ecosystem food webs. Weather patterns in the Carboniferous world create flying conditions that modern pilots would recognize as nearly ideal. The absence of strong temperature gradients between equatorial and polar regions minimizes atmospheric turbulence. High humidity reduces thermal updrafts and downdrafts that might destabilize large flying organisms. Consistent atmospheric pressure supports predictable flight performance across different altitudes and geographic regions. The daily routine of an individual Meganeura follows patterns dictated by both physiological needs and environmental opportunities. Dawn hunting sessions take advantage of cool air temperatures and reduced wind speeds. Midday hours often involve territorial patrols and interactions with conspecifics. Evening hunting capitalizes on increased activity among prey species, emerging for their own feeding periods. Night brings rest periods spent clinging to vegetation in protected locations that offer shelter from potential predators and environmental hazards. As the giant dragonfly continues its patrol through dappled sunlight and oxygen-rich air, its presence embodies the temporary suspension of normal biological rules that characterizes this ancient era. Each wing beat propels it through an atmosphere that will never again support such magnificent aerial arthropods. Each hunting flight writes another line in the story of life's brief experiment with insect gigantism. The forest below rustles with other movements, other giants making their own patient way through a world built for ambitious scale. But in the canopy, in the realm of flight and light and endless aerial highways, Meganeura reigns as undisputed master of an evolutionary moment that spans millions of years yet remains, in geological terms, as brief as a single breath. The fallen log stretches 30 meters through the understory, its bark-covered surface serving as an elevated highway for creatures that navigate the forest floor with methodical precision. Arthropleura armata moves along this natural bridge with the unhurried confidence of an organism that has grown too large for most predators to consider as prey. 2 meters of segmented body flows across the decaying wood like a living train, each of its dozens of legs finding purchase on the textured bark with mechanical certainty. The millipedes body plan represents one of evolution's most successful experiments in modular construction. Each segment carries its own pair of legs, its own set of muscles, its own neural ganglia that coordinate movement with neighboring segments. The result is a locomotion system that distributes mechanical stress across multiple points of contact, allowing the creature to traverse uneven terrain that would challenge organisms dependent on fewer, more specialized limbs. The segmented architecture also permits remarkable flexibility, enabling Arthropleura to navigate around obstacles that would block the path of more rigid body forms. Beneath the chitinous exoskeleton snubs, respiratory systems operate at scales that push the limits of arthropod physiology. Spiracles positioned along each segment open into tracheal networks that branch repeatedly as they penetrate deeper into body tissues. In smaller millipedes, simple diffusion drives gas exchange, But Arthropleura requires active ventilation to move oxygen through the extended distances of its massive form. Specialized muscles compress and expand body segments in rhythmic patterns that pump air through the internal airways like a biological bellows. The dietary preferences of these giant millipedes focus primarily on decomposing plant material, though their size permits occasional predatory behavior that smaller relatives cannot achieve. Powerful mandibles process fallen leaves, rotting wood, and the occasional small arthropod that ventures too close to the feeding apparatus. The digestive system extends through most of the body length, with specialized chambers that break down cellulose and extract nutrients from plant materials that resist decomposition in the humid Carboniferous climate. Scientists studying Arthropleura fossil remains encounter one of paleontology's most intriguing preservation challenges. The soft tissues that comprise much of the millipede's internal anatomy rarely fossilize, leaving researchers to infer physiological capabilities from fragmentary exoskeleton pieces in comparison with modern relatives. Complete specimens, when discovered, provide crucial insights into body proportions and segmentation patterns that inform understanding of how such large arthropods managed basic biological functions. Only took 40 million years for millipede ancestors to evolve from marine forms into these terrestrial giants. Only took changing atmospheric conditions to eventually constrain their size back to dimensions that modern ecosystems recognize. Only took the patience of geological time to create and then eliminate one of the most impressive examples of arthropod engineering in Earth's history. The forest floor environment that supports Arthropleura populations creates a complex three-dimensional habitat where vertical and horizontal surfaces merge into continuous pathways. Fallen trees provide elevated roots above the waterlogged soil that dominates much of the Carboniferous landscape. Root systems create natural bridges between distant points. The accumulated debris of countless growing seasons forms deep layers of organic matter that offer both food resources and protective shelter for organisms adapted to life in the decomposer community. Chemical communication plays a crucial role in Arthropleura's social behavior. Though the precise mechanisms remain mysterious to researchers studying fossil evidence, specialized glands located along the body segments likely produce pheromone compounds that mark territorial boundaries, indicate reproductive status, and coordinate group movements during migration periods. The chemical signatures persist in the humid environment longer than they would under drier conditions, creating information networks that span considerable distances through the forest ecosystem. Molting represents one of the most vulnerable periods in the Arthropleura life cycle. The process of shedding and replacing the exoskeleton requires weeks of preparation, followed by hours of exposure in a soft, defenseless state. Individuals seek protected locations beneath fallen logs or in natural depressions, where they can remain hidden during the molting process. The discarded exoskeletons, rich in calcium and other minerals, become food resources for smaller arthropods and contribute to the nutrient cycling that sustains forest productivity. The territorial range of individual Arthropleura encompasses several hectares of forest floor. Though population densities remain relatively low due to the substantial food requirements of such large organisms, home ranges overlap at their boundaries, creating zones where different individuals encounter each other during foraging expeditions. These interactions follow ritualized patterns that minimize direct competition, while establishing dominance hierarchies based on size and age rather than aggressive confrontation. Predation pressure on adult Arthropleura comes primarily from the largest amphibians that share their forest habitat. Though even these predators approach such formidable prey with considerable caution, the defensive capabilities of giant millipedes include chemical deterrents produced by specialized glands, the ability to curl into a protective spiral that presents only armored surfaces to attackers, and sheer size that makes handling difficult for most potential predators. The reproductive cycle follows seasonal patterns tied to environmental conditions that optimize survival of vulnerable juvenile stages. Mating occurs during periods of stable weather when food resources are abundant and environmental stresses remain minimal. Females deposit eggs in protected locations where developing young can access adequate food while remaining hidden from predators that specialize in hunting smaller arthropods. Juvenile Arthropleura begin life as miniature versions of their parents, adding segments and increasing size through successive molts over a period of several years. Growth rates depend heavily on food availability and environmental conditions, with some individuals requiring a decade or more to reach full adult size. This extended development period means that populations include individuals representing multiple age classes, each occupying slightly different ecological niches within the forest ecosystem. The ecological impact of these giant millipedes extends far beyond their role as decomposers. Their burrowing activities aerate soil layers and create microhabitats that benefit smaller organisms. Their waste products contribute essential nutrients to soil chemistry. Their movement patterns help distribute fungal spores and other microscopic organisms throughout the forest floor community. As Arthropleura continues its methodical journey across the fallen log, pausing occasionally to investigate promising deposits of decaying organic matter. Its presence exemplifies the patient rhythms that characterize life in the Carboniferous forests. No urgency drives its movements. No predators force rapid escapes. No competition demands aggressive territorial defense. Instead, the giant millipede embodies the unhurried confidence of an organism perfectly adapted to an environment that rewards steady persistence over dramatic action. The bark beneath its feet tells its own story of deep time, marked by the growth rings of a tree that lived for centuries before contributing its body to the forest floor community. Now it serves as highway and habitat for creatures whose own stories will be written in stone, preserved for future scientists to puzzle over in laboratories that exist hundreds of millions of years in the unimaginable future. The shallow seas retreat and advance with tidal predictability, leaving behind mudflats that glisten under the Carboniferous sun like vast mirrors reflecting an alien sky. In these margins between land and water, life conducts its most ambitious experiments, testing the boundaries between aquatic heritage and terrestrial possibility. The Eurypterids patrol these transitional zones with the confidence of apex predators, their paddle-like appendages propelling them through water that barely covers their armored backs, creating ripples that spread across the surface like liquid echoes of ancient power. Pterygotus reaches lengths that dwarf modern marine arthropods, its segmented body stretching over 2 meters from the compound eyes that crown its flattened head to the telson that serves as both rudder and weapon. The creature moves through brackish waters with mechanical efficiency, each stroke of its swimming appendages calculated to conserve energy while maintaining the steady forward progress that characterizes successful predation in environments where prey remains scarce and scattered across vast underwater territories. The morphology of these giant sea scorpions represents evolutionary engineering pushed to its functional limits. The flattened body plan provides hydrodynamic efficiency while maximizing surface area for the book-gill respiratory systems housed beneath protective segments. Specialized swimming paddles, modified from walking legs, generate thrust through figure-8 patterns that minimize turbulence while maximizing forward propulsion. The result is a locomotion system that operates with the calculated precision of a biological submarine. The respiratory system that sustains such massive aquatic arthropods operates through book gills housed in protective chambers beneath the body segments. These structures, evolutionary precursors to the book lungs found in terrestrial arachnids, extract dissolved oxygen from water with remarkable efficiency. Each gill book consists of hundreds of thin lamellae that create enormous surface areas for gas exchange. Yet even in the oxygen-rich waters of carboniferous seas, the physics of diffusion place upper limits on body size that Pterygotus approaches but cannot exceed. Water circulation through the gill chambers requires active pumping mechanisms that consume significant metabolic energy. Specialized muscles compress and expand the protective opercula that cover the gill bugs, creating pressure differentials that drive fresh water across the respiratory surfaces. This active ventilation system enables larger body sizes than would be possible with passive diffusion alone. Yet, it also creates energetic constraints that influence feeding behavior and territorial strategies. Scientists studying eurypterid fossils encounter preservation conditions that reveal extraordinary detail about these ancient predators. Fine-grained sediments deposited in quiet water environments capture not only the hard exoskeleton but occasionally preserve traces of soft tissues, including muscle attachments, digestive tract contents, and even delicate gillbook structures. These exceptional specimens provide insights into feeding behavior, growth patterns, and ecological relationships that transform abstract fossil forms into dynamic components of ancient ecosystems. The preservation process itself offers clues about ancient environmental conditions. Rapid burial in anoxic sediments prevents bacterial decomposition, while the mineral composition of surrounding sediments influences the chemical processes that replace organic materials with stone. Pyrite crystals often form within preserved soft tissues, creating metallic traceries that outline internal anatomical structures with startling clarity. The hunting strategy employed by these giant sea scorpions combines patience with explosive bursts of activity that can capture prey items, ranging from smaller arthropods to early vertebrates. Pterygotus establishes territories along productive shorelines where potential prey concentrate during feeding or reproductive periods. The compound eyes, positioned on top of the flattened head, provide excellent visibility while the predator lies partially buried in sediment, creating an ambush platform that maximizes surprise while minimizing energy expenditure. Attack sequences unfold with mechanical precision, honed by millions of years of predatory evolution. The initial strike involves rapid acceleration toward detected prey, followed by grasping motions that bring victims within range of the powerful chelicerae that function as both capture tools and processing equipment. The biomechanics of these attacks require split-second coordination between visual detection, neural processing, and muscular response systems that operate at the limits of arthropod neural capacity. Only took 50 million years for eurypterids to evolve from smaller marine ancestors into these shallow water giants. Only took changing ocean chemistry and the rise of vertebrate predators to eventually drive them toward extinction. Only took the patient work of evolutionary time to create and then eliminate one of the most formidable groups of aquatic arthropod predators in geological history. Meanwhile, on the expanding land surfaces that surround these productive coastal waters, insects begin their first tentative experiments with flight and freedom from aquatic constraints. The earliest winged insects emerge from this period as small, delicate creatures whose flight capabilities barely extend beyond short gliding movements between elevated perches. Yet these modest beginnings contain the evolutionary potential that will eventually produce the aerial giants that dominate Carboniferous skies. The transition from aquatic to terrestrial life represents one of the most challenging evolutionary hurdles in arthropod history. Respiratory systems designed for extracting oxygen from water must be modified to function in air through fundamental reorganization of gas exchange surfaces. Structural support systems adequate for bodies supported by water density must be strengthened to function under the full weight of gravity. Sensory systems adapted for aquatic environments must develop new capabilities for navigation in three-dimensional aerial environments. Early flying insects solve these challenges through incremental modifications to existing body plans rather than revolutionary redesigns. Wings developed from gill plates that originally functioned in aquatic respiration, repurposed through evolutionary processes that demonstrate the opportunistic nature of natural selection. The transformation involves gradual changes in tissue structure, vascular patterns, and muscular attachments that occur over thousands of generations. Flight muscles evolve from swimming muscles, maintaining many of the same neural control patterns while adapting to the different mechanical requirements of aerial locomotion. The neural architecture that coordinates swimming strokes becomes the foundation for flight control systems. Though the computational demands of three-dimensional aerial navigation require significant expansions in processing capacity and sensory integration, the atmospheric conditions that will eventually permit giant flying insects already exist during this transitional period. But the evolutionary innovations necessary to exploit these conditions require millions of years of gradual refinement. Wing design must be optimized for different flight speeds and maneuvers through iterative improvements in membrane structure, vane architecture, and aerodynamic efficiency. Neural control systems must develop the computational power necessary to coordinate complex flight patterns while processing visual information from compound eyes adapted for aerial navigation. Metabolic systems must adapt to the energy demands of sustained aerial activity, which exceed those of terrestrial locomotion by orders of magnitude. The development of more efficient oxygen delivery systems, enhanced fat storage capabilities, and improved muscle biochemistry all contribute to the evolutionary innovations that make sustained flight possible in arthropod body plans originally designed for aquatic or terrestrial locomotion. Fossil evidence for early insect flight remains frustratingly incomplete, as the delicate wing membranes rarely preserve in the geological record. Paleontologists studying this crucial period rely heavily on indirect evidence, including the ecological changes that accompany the appearance of flying insects and comparative studies of primitive wing structures in surviving insect lineages. The result is a partial picture of one of evolution's most significant innovations. The ecological impact of early flying insects extends far beyond their immediate predatory relationships. Their ability to disperse rapidly across landscapes accelerates gene flow between isolated populations, promoting evolutionary innovation and adaptation to local environmental conditions. Their capacity for three-dimensional movement creates new ecological niches that were previously unavailable to terrestrial arthropods, opening up canopy habitats and aerial food webs that increase ecosystem complexity. Predation pressure from eurypterids in aquatic environments may actually accelerate the evolution of flight capabilities in insects. Individuals capable of escaping from water into aerial environments gain access to refuge habitats where aquatic predators cannot follow. This creates strong selective pressure favoring any morphological or behavioral modifications that improve aerial mobility, even if those modifications initially provide only marginal advantages over purely terrestrial locomotion. The chemical composition of Carboniferous seawater differs significantly from modern ocean chemistry, with higher concentrations of dissolved minerals and different ratios of major ionic components. These conditions affect the physiology of marine organisms in subtle ways that influence growth rates, metabolic efficiency, and evolutionary trajectories. Eurypterids living in these ancient seas operate under chemical constraints that no longer exist in contemporary marine environments. Temperature patterns in Carboniferous oceans remain remarkably stable compared to the dramatic fluctuations that characterize later geological periods. The absence of polar ice caps eliminates one major source of oceanic temperature variation, while the configuration of continental landmasses creates circulation patterns that distribute heat more evenly across different ocean basins. These stable conditions support the complex life cycles that characterize large marine arthropods. The daily routine of a pterygotus individual follows patterns dictated by both tidal cycles and the behavioral rhythms of prey species. Dawn hunting sessions take advantage of reduced visibility that allows closer approach to potential prey while minimizing detection by competitors. Midday periods often involve territorial maintenance and interaction with conspecifics, including ritualized displays that establish dominance hierarchies without the energy costs of direct combat. Evening hunting capitalizes on increased activity among smaller arthropods, emerging from protective hiding places to feed in the nutrient-rich waters of tidal zones. Night brings rest periods spent in protected locations that offer security from larger predators, while maintaining access to territorial boundaries that must be defended against encroachment. Molting represents a particularly vulnerable period for these large aquatic arthropods. The process requires finding protected locations where individuals can remain hidden during the hours of soft-bodied vulnerability that follow exoskeleton shedding, rocky overhangs, dense vegetation, and deep-water refugia provide the security necessary for successful molting. Though mortality rates during these periods remain high despite careful site selection. As the Eurypterid continues its patrol through sun-dappled shallows, its presence embodies the ancient relationship between predator and prey that shapes evolutionary trajectories across geological time. Above the water surface, primitive insects begin their first experimental flights through air that will eventually support aerial arthropods of unprecedented size. The stage is set for transformations that will redefine the limits of arthropod existence on both land and sea. The interface between water and air shimmers with possibility, holding the promise of evolutionary innovations that will transform Earth's biological landscape in ways that no single species can anticipate or control. The chemistry of growing large operates according to principles that seem to mock the constraints imposed on modern arthropods. Oxygen molecules drift through tracheal networks with the abundance of a planetary gift, dissolving into hemolymph and reaching tissues that in contemporary insects would struggle to receive adequate supplies. The fundamental equation that governs arthropod size, the relationship between oxygen delivery and metabolic demand, shifts dramatically in favor of biological ambition when atmospheric concentrations nearly double the modern baseline. Spiracles along the exoskeleton open wider than their modern counterparts, revealing internal architectures designed to exploit atmospheric abundance rather than conserve scarce resources. Each opening leads to branching networks of tubes that penetrate deeper into body tissues, carrying oxygen directly to working muscles without the intermediate steps required by vertebrate circulatory systems. The efficiency of this direct delivery system becomes magnified when the source medium contains such unprecedented concentrations of the essential gas. The physics of diffusion follows mathematical laws that remain constant across geological time. Yet the practical implications of these laws change dramatically when concentration gradients increase. Oxygen moves from areas of high concentration to areas of low concentration, at rates proportional to the steepness of the gradient. In carboniferous atmospheres, this gradient becomes so steep that passive diffusion alone can sustain metabolic processes in tissues located far from respiratory surfaces. Scientists studying the respiratory physiology of giant carboniferous arthropods work with fossilized remains that preserve tantalizing hints about internal anatomy. Impressions of tracheal systems occasionally appear in fine-grained sediments, revealing branching patterns that differ significantly from those found in modern insects. The preserved evidence suggests respiratory networks that penetrate more deeply into body cores, with larger diameter tubes that could accommodate greater gas flow volumes. Active ventilation supplements passive diffusion in the largest arthropod forms, though the mechanisms remain partially mysterious to researchers studying ancient physiology. Specialized muscles compress and expand body segments in rhythmic patterns that pump air through the internal tube networks like biological bellows. This active breathing represents a significant departure from the purely passive gas exchange that characterizes smaller contemporary arthropods. Only took atmospheric chemistry millions of years to create conditions that temporarily suspended normal size constraints. Only took another few million years for those same atmospheric conditions to begin their slow retreat toward modern levels. Only took the patient work of planetary evolution to open and then close a window of biological possibility that arthropods will never again encounter. The metabolic machinery that powers giant arthropod bodies operates at intensities that approach theoretical limits for arthropod biochemistry. Cellular respiration processes that in modern insects run at modest efficiency levels accelerate dramatically when supplied with abundant oxygen. Mitochondrial activity increases proportionally, generating energy at rates that support larger muscle masses, more complex behaviors, and extended periods of high activity. Muscle fibers and giant carboniferous arthropods develop architectures that exploit the enhanced oxygen availability. Flight muscles in particular show modifications that increase contractile power while maintaining the rapid contraction rates necessary for wing operation. The biochemical pathways that convert oxygen and nutrients into mechanical energy operate with efficiency levels that modern arthropods cannot achieve under contemporary atmospheric conditions. Heat production becomes a significant physiological challenge for large arthropods operating high-intensity metabolisms in humid, carboniferous environments. The same metabolic processes that enable giant size also generate thermal loads that must be dissipated to prevent overheating. Behavioral adaptations include seeking shade during peak temperature periods and timing activity cycles to coincide with cooler portions of the daily temperature cycle. Circulatory systems in giant arthropods show modifications that improve the distribution of nutrients and waste products throughout enlarged body volumes. While arthropods lack the closed circulatory systems found in vertebrates, their open hemolymph systems develop enhanced pumping mechanisms and improved flow patterns that serve the needs of larger body masses. Specialized chambers within the hemocule create circulation patterns that reach peripheral tissues more effectively. The scaling relationships that govern biological systems create challenges that giant arthropods solve through innovative modifications to basic body plans. Surface area increases as the square of linear dimensions, while volume increases as the cube, creating mismatches between oxygen uptake capacity and metabolic demand that require creative solutions. Enhanced respiratory surface areas, modified circulation patterns, and behavioral adaptations all contribute to making giant size feasible. Exoskeleton architecture must adapt to support larger body masses while maintaining flexibility necessary for movement. The chitin protein composite that forms arthropod external skeletons becomes thicker and develops internal reinforcement structures that distribute mechanical loads more effectively. Joint mechanisms require modification to handle the increased forces generated by larger muscle masses operating longer lever arms. Nervous system architecture scales up to coordinate the complex behaviors required for survival at giant size. Neural processing centers expand to handle increased sensory input from larger compound eyes and more extensive mechanoreceptor networks. Motor control systems develop enhanced precision to coordinate the movements of numerous leg segments and wing control muscles with the accuracy required for successful predation and navigation. Digestive systems show modifications that accommodate the increased food requirements of larger body masses while maintaining processing efficiency. Gut capacity increases proportionally to body size, while specialized chambers develop enhanced mechanical and chemical breakdown capabilities. Nutrient absorption surfaces expand through increased folding and the development of specialized absorption zones that extract maximum nutrition from available food sources. Growth patterns in giant arthropods follow extended developmental schedules that span multiple years from hatching to reproductive maturity. Molting cycles become less frequent but involve larger size increases between successive instars. The extended juvenile period allows time for the gradual development of physiological systems capable of supporting giant adult forms while minimizing the metabolic costs of rapid growth. Thermoregulation strategies become increasingly important as body size increases and surface-to-volume ratios decrease. Giant arthropods develop behavioral patterns that exploit environmental temperature variation to maintain optimal body temperatures. Morning basking sessions warm flight muscles to operating temperatures, while shade-seeking behavior during hot periods prevents overheating that could damage temperature-sensitive enzyme systems. Water balance presents unique challenges for large arthropods living in humid, carboniferous environments. Increased body size creates larger water storage capacity, but also increases absolute water loss rates through respiratory surfaces. Specialized water conservation mechanisms develop to maintain proper hydration levels while accommodating the high respiratory rates required to support enhanced metabolisms. The biomechanics of locomotion require fundamental modifications to accommodate increased body mass and altered body proportions. Leg structures become more robust to support greater weight loads, while joint mechanisms develop enhanced range of motion to maintain agility despite increased size. Walking gaits adapt to distribute weight more effectively across multiple contact points with substrate surfaces. Wing loading calculations reveal the aerodynamic challenges faced by giant flying arthropods operating in carboniferous atmospheric conditions. While increased oxygen concentration improves metabolic support for flight muscles, the fundamental physics of lift generation require larger wing areas to support increased body masses. Wing membrane architecture develops enhanced structural support while maintaining the flexibility necessary for controlled flight. As the chemistry of life operates under these temporarily relaxed constraints, every cellular process becomes an experiment in biological possibility. The same fundamental biochemical pathways that sustain modern arthropods accelerate and intensify, creating metabolic environments that support body sizes and activity levels that later atmospheric conditions will render impossible. The abundance flows through every respiratory surface, every mitochondrial membrane, every neural pathway that coordinates the complex behaviors of organisms grown large on planetary generosity that spans millions of years yet remains, in geological terms, as temporary as a single season. Forests that forgot to rot stretch across landscapes that measure in continents rather than kilometers. Their accumulated biomass creating carbon reservoirs that will reshape planetary chemistry for hundreds of millions of years. The tree ferns and early conifers that dominate these ancient woodlands produce lignin-rich tissues that resist decomposition in ways that modern forest ecosystems cannot replicate. Fallen trunks lie where they collapse, their woody tissues accumulating in layers that grow deeper with each passing century. The biochemistry of decay operates under different rules in these carboniferous wetlands. Bacteria and fungi that specialize in breaking down complex organic molecules have not yet evolved the enzymatic pathways necessary to efficiently process lignin, the structural polymer that gives woody plants their strength. The result is organic matter that accumulates faster than it decomposes, creating vast deposits of partially decayed plant material that remove carbon from the atmospheric reservoir. Waterlogged conditions in the extensive swamplands create anaerobic environments where decomposition slows to geological timescales. Organic matter becomes buried beneath successive layers of sediment before bacterial processes can return its carbon to the atmosphere as carbon dioxide. The chemistry of preservation favors the formation of peat deposits that will eventually transform into coal seams through the pressure and heat of geological time. Scientists studying Carboniferous coal deposits find evidence of this biological revolution preserved in microscopic detail. Plant cell walls, woody tissues, and even delicate leaf structures appear in fossilized form, revealing the anatomy of forests that operated according to principles fundamentally different from modern ecosystems. The preservation process itself tells the story of carbon burial on scales that dwarf contemporary carbon cycling. Only took bacterial evolution several million years to catch up with plant innovation, developing enzymes capable of efficient lignin breakdown. Only took that biochemical advancement to end the era of massive carbon burial that characterized the Carboniferous period. Only took the patient work of evolutionary time to solve the decomposition puzzle and restore balance to the carbon cycle. The accumulating organic matter creates habitat layers that support complex communities of decomposer organisms working at the limits of their biochemical capabilities. Fungal networks spread through the partially decayed wood, extracting nutrients through enzymatic processes that operate with modest efficiency compared to their modern counterparts. Arthropod communities specialize in mechanical breakdown of organic matter, compensating for the limited chemical decomposition through physical fragmentation. Soil formation processes operate differently when organic matter accumulates faster than it breaks down. Nutrient cycling becomes constrained by the slow release of essential elements from resistant organic compounds. Plant communities adapt to these nutrient-poor conditions through symbiotic relationships with mycorrhizal fungi and specialized root architectures that maximize extraction of available minerals. The three-dimensional structure of these accumulating forests creates habitat complexity that increases dramatically over time. Standing dead trees provide nesting sites and elevated highways for arthropod communities. Fallen logs create elevated pathways above waterlogged forest floors. The accumulated organic matter forms deep, spongy substrates that support specialized plant communities adapted to life on decaying wood. Water chemistry in carboniferous swamplands reflects the massive inputs of organic matter from inadequately decomposed plant materials. Dissolved organic compounds create acidic conditions that affect the physiology of aquatic organisms while influencing mineral solubility and nutrient availability. The water itself becomes a weak organic acid that slowly dissolves mineral substrate and creates unique chemical environments. Fire ecology operates under constraints imposed by high atmospheric oxygen concentrations and abundant organic fuel loads. When fires do occur, they burn with intensities that consume vast areas before encountering natural fire breaks. The combination of oxygen-rich air and accumulated organic matter creates combustion conditions that modern firefighting techniques would struggle to control. The peat-forming processes that characterize carboniferous swamplands require specific hydrological conditions that maintain water levels above the organic matter surface while preventing complete inundation. Seasonal fluctuations in water level create alternating periods of growth and partial decomposition that build up the layered deposits characteristic of coal-forming environments. Chemical processes in the accumulating organic matter follow pathways that gradually transform plant tissues into hydrocarbon compounds. The biochemical transformations occur slowly under anaerobic conditions, with temperature and pressure playing increasingly important roles as burial depth increases. These early stages of the coal formation process remove vast quantities of carbon from the active atmospheric reservoir. Atmospheric carbon dioxide concentrations decline gradually as organic matter accumulation outpaces decomposition across continental-scale forest ecosystems. The chemical weathering of exposed rock surfaces also contributes to atmospheric carbon removal. But the biological processes dominating carboniferous swamplands represent the primary mechanism driving atmospheric change during this critical period. Plant community succession in these slowly decaying forests follows patterns that extend across multiple centuries. Pioneer species colonize exposed mineral surfaces, while later successional communities adapt to life on increasingly thick accumulations of organic matter. The result is forest ecosystems with temporal dimensions that exceed those of modern plant communities by orders of magnitude. Nutrient limitation becomes increasingly severe as essential elements become locked in resistant organic compounds that resist bacterial and fungal breakdown. Nitrogen, phosphorus, and other critical nutrients accumulate in forms that remain unavailable to living plants, despite their physical presence in the environment. This creates selection pressure for plant species capable of efficient nutrient conservation and recycling. The mechanical properties of partially decomposed organic matter create substrates that combine some characteristics of soil with some characteristics of living tissue. Root systems develop specialized architectures for penetrating and anchoring in these unusual substrates, while mechanical support structures adapt to the reduced stability provided by organic rather than mineral soil foundations. Hydrology in peat-forming environments creates water flow patterns that differ significantly from those in mineral soil ecosystems. Water movement through organic substrates follows different physical principles than flow through sand and clay particles. The result is watershed-scale hydrological systems that operate according to unique principles that disappeared when efficient lignin decomposition evolved. As these ancient forests continue their patient work of carbon burial, they reshape planetary chemistry in ways that will influence Earth's climate system for hundreds of millions of years. Each fallen tree that resists decay removes atmospheric carbon that might otherwise contribute to greenhouse warming. Each layer of accumulated organic matter represents another step in the process that will eventually constrain atmospheric chemistry and end the era of arthropod gigantism. The forests grow and fall and grow again, building carbon monuments to an age when life learned to construct faster than it could destroy. When the balance between production and decomposition tilted toward accumulation on scales that transform the chemistry of entire worlds. The spider's expanding territory encompasses forest floor domains that measure in hectares, rather than the modest home ranges that constrain modern arachnids. Megarachne moves through the understory with the deliberate precision, its massive form navigating between fallen logs and standing tree trunks, with the patient confidence of an organism that has grown beyond the reach of most potential predators. 8 legs coordinate in fluid motion patterns that distribute the creature's substantial weight across multiple contact points, preventing the penetration damage that might result from concentrated pressure on the soft organic substrates that carpet the forest floor. Body length approaches half a meter in the largest specimens, though recent scientific investigations suggest that early estimates may have overstated the actual dimensions of these ancient arachnids. Nevertheless, even conservative size estimates place Megarachne among the largest terrestrial arthropods of the Carboniferous period, a testament to the atmospheric conditions that temporarily relax the constraints that limit arthropod body size in contemporary ecosystems. The exoskeleton architecture required to support such massive arachnid forms represents engineering solutions that push the limits of chitinous construction materials. Load-bearing structures become thicker and develop internal reinforcement patterns that distribute mechanical stresses more effectively than the simpler architectures found in smaller relatives. Joint mechanisms require enhanced flexibility to accommodate the increased forces generated by larger muscle masses, while maintaining the precision necessary for coordinated locomotion. Scientists studying Megarachne fossils encounter preservation challenges that complicate efforts to understand the ecology and behavior of these ancient giants. The relatively delicate nature of arachnid exoskeletons makes complete fossil specimens rare, while the terrestrial environments where these creatures lived provide less favorable fossilization conditions than the aquatic settings that preserve marine arthropods with greater fidelity. The respiratory system that sustains such large arachnid bodies operates through book lungs that represent scaled-up versions of the respiratory structures found in modern spiders. These organs consist of numerous thin sheets of tissue arranged in parallel layers that create extensive surface areas for gas exchange with atmospheric air. The enhanced oxygen concentrations available in Carboniferous atmospheres enable these respiratory structures to support metabolic processes in body masses that exceed modern arachnid limits by orders of magnitude. Only took atmospheric oxygen concentrations several million years to reach levels that enabled such impressive arachnid size. Only took subsequent atmospheric changes to gradually constrain spider body size back to dimensions that modern ecosystems recognize. Only took the patient work of evolutionary time to open and then close a window of arachnid possibility that will never reopen. Meanwhile, smaller arachnids begin experimenting with aerial web construction techniques that exploit the three-dimensional architecture created by Carboniferous forest structure. These early web builders produce silk with mechanical properties similar to those found in modern spiders. Yet they deploy this remarkable material in patterns that take advantage of the unique environmental conditions that characterize ancient forest ecosystems. The first aerial webs appear as simple platforms stretched between convenient anchor points, serving primarily as substrate extensions that allow spiders to hunt in locations removed from direct ground contact. These primitive constructions lack the geometric sophistication that will characterize later web designs. Yet they represent crucial evolutionary innovations that expand the ecological niches available to arachnid predators. Web construction in Carboniferous forests faces environmental challenges that differ significantly from those encountered by modern web-building spiders. High humidity levels affect silk mechanical properties, while the absence of strong wind patterns reduces some of the structural stresses that influence contemporary web architecture. The result is web designs that prioritize capture efficiency over structural resilience. Silk production in these early aerial web builders requires metabolic investments that represent significant portions of total energy budgets. The proteins that comprise spider silk contain high concentrations of amino acids that must be obtained from dietary sources or synthesized through metabolic processes that consume considerable energy. Successful web construction depends on adequate nutrition to support both silk production and the extended waiting periods that characterize ambush predation strategies. Prey capture efficiency in aerial webs depends heavily on the flight patterns and behavioral characteristics of early flying insects. The primitive flight capabilities of Carboniferous insects create capture opportunities that may not exist for insects with more sophisticated aerial maneuvers. Web placement strategies evolve to exploit the predictable flight paths that connect feeding areas, resting sites, and reproductive territories. The chemical properties of Carboniferous atmospheric moisture affect silk adhesion mechanisms in ways that require behavioral adaptations by web-building spiders. Higher humidity levels maintain silk flexibility for extended periods, while also affecting the adhesive properties of capture spirals. Web maintenance schedules adapt to these environmental conditions through behavioral patterns that optimize capture efficiency while minimizing silk replacement costs. Territorial behavior in large ground-dwelling spiders like Meganeura involves chemical marking systems that establish boundaries across substantial areas of forest habitat. Specialized glands produce pheromone compounds that persist in the humid environment for extended periods, creating chemical landscapes that communicate territorial ownership to potential competitors. These chemical signals reduce the frequency of direct confrontations that could result in injury to valuable hunting appendages. Hunting strategies employed by giant spiders combine elements of ambush predation with active pursuit tactics that exploit their enhanced size and speed. Patient waiting periods allow prey to approach within striking distance, while rapid pursuit capabilities enable capture of prey items that detect the predator's presence before entering optimal ambush range. The combination provides hunting flexibility that increases overall prey capture success rates. Molting represents a particularly vulnerable period for large arachnids, requiring secure hiding places and extended periods of immobility while new exoskeletons harden to functional strength. The process becomes increasingly risky as body size increases, due to both the extended duration required for larger exoskeletons to achieve full hardness and the increased conspicuousness that makes detection by predators more likely. Reproductive behavior in giant Carboniferous spiders involves elaborate courtship rituals that minimize the risks associated with sexual cannibalism in species where females substantially outweigh males. Chemical communication signals indicate reproductive readiness while reducing the likelihood of predatory attacks on approaching males. Specialized courtship behaviors exploit vibrational communication through substrate contact and silk-mediated signals. The ecological impact of large predatory arachnids extends throughout forest food webs, influencing prey population dynamics and evolutionary trajectories for multiple arthropod lineages. Predation pressure from spiders affects activity patterns, habitat selection, and anti-predator adaptations in prey species, creating cascading effects that influence entire ecosystem structures. As Meganeura continues its methodical exploration of forest floor territories, and smaller relatives experiment with aerial web construction in the canopy above, the arachnid lineage writes another chapter in the story of arthropod innovation during Earth's brief experiment with atmospheric abundance. Each step across the organic forest floor, each strand of silk stretched between anchor points, contributes to the expansion of arachnid ecological influence during an era when size limitations temporarily relaxed their constraints on biological ambition. The forest floor rustles with the movements of creatures that will never again achieve such impressive dimensions. Their presence testimony to the temporary intersection of atmospheric chemistry and evolutionary opportunity that defines the Carboniferous period. When scorpions hunted on land, the transition from aquatic to terrestrial predation represented one of evolution's most audacious experiments in arthropod redesign. These ancient arachnids emerged from shallow waters onto mudflats that glisten under the alien atmosphere, their bodies adapting to terrestrial life one molting cycle at a time through modifications that accumulate across generations like biological amendments to an ancestral blueprint. The exoskeleton that once provided protection against aquatic pressures now must function as structural support against the full weight of gravity, Cuticle thickness increases gradually through successive molts, while internal architecture develops reinforcement patterns that distribute mechanical loads more effectively than the simpler designs adequate for aquatic environments. The transformation occurs slowly, each new exoskeleton representing another incremental step toward full terrestrial capability. Book gills that extracted oxygen from water undergo fundamental reorganization to function as air-breathing organs. The delicate lamellae that once filtered dissolved gases from aquatic medium develop protective chambers that prevent desiccation while maintaining the extensive surface areas necessary for efficient gas exchange. This respiratory revolution enables extended forays onto land surfaces that previously remained inaccessible to arthropod predators. Scientists studying the transition from aquatic to terrestrial scorpions encounter fossil evidence that reveals both the gradual nature of this evolutionary transformation and the environmental pressures that drove it. Trace fossils preserve evidence of early terrestrial behavior, including burrow systems and trackways that document the expanding territorial ranges of scorpions adapting to life on land. The sensory systems that guided underwater navigation require extensive modification to function in aerial environments. Mechanoreceptors that once detected water currents and pressure changes adapt to sense airborne vibrations and substrate movements. Chemical detection systems develop enhanced sensitivity to airborne pheromones and prey-related odors that provide information about terrestrial hunting opportunities. Only took atmospheric pressure differences several million years to create conditions favoring terrestrial arthropod expansion. Only took subsequent climate changes to modify the environmental pressures that shaped early terrestrial adaptation. Only took evolutionary time's patient work to transform aquatic predators into some of the most successful terrestrial arthropod hunters in Earth's history. Locomotion systems designed for underwater movement face fundamental challenges when operating against gravitational forces in aerial environments. Leg structures strengthen through successive molts, developing enhanced muscle attachments and joint mechanisms that provide greater mechanical advantage for terrestrial movement. Walking gaits evolve to distribute weight more effectively across multiple contact points with substrate surfaces. The hydraulic systems that power scorpion movement require modification to function efficiently in terrestrial environments, where water conservation becomes a critical physiological constraint. Hemolymph circulation patterns adapt to maintain adequate pressure for leg extension while minimizing fluid loss through respiratory surfaces. Specialized behavioral adaptations help maintain proper hydration levels during extended terrestrial hunting expeditions. Predatory strategies that evolved for aquatic environments undergo substantial modification to accommodate the different prey communities and environmental conditions that characterize terrestrial ecosystems. Ambush tactics that relied on water cover and current patterns adapt to exploit terrestrial hiding places and prey movement patterns. Capture techniques develop enhanced precision to accommodate the different biomechanics of prey restraint in aerial versus aquatic media. Venom delivery systems that evolve for underwater prey capture require adjustments to function effectively against terrestrial prey items. Chemical compositions adapt to accommodate physiological differences between aquatic and terrestrial prey species, while delivery mechanisms develop enhanced precision to compensate for the different behavioral responses of prey organisms operating in aerial environments. Territorial behavior in terrestrial scorpions involves chemical marking systems that establish boundaries across substantial areas of suitable habitat. Pheromone production and detection capabilities evolve to function in aerial rather than aquatic chemical environments, creating communication systems that operate effectively across the three-dimensional terrestrial landscapes that early scorpions begin to exploit. The burrowing behavior that will become characteristic of many scorpion lineages develops as an adaptation to terrestrial environmental stresses. Excavation techniques evolve to create shelter systems that provide protection from predators, environmental extremes, and desiccation risks that do not exist in aquatic environments. These underground retreats become crucial components of terrestrial survival strategies. Reproductive cycles adapt to terrestrial environmental conditions through modifications that protect developing young from the enhanced environmental stresses that characterize life outside aquatic media. Brooding behaviors evolve to provide maternal protection during vulnerable developmental stages, while birth timing adapts to seasonal patterns that optimize survival chances for terrestrial offspring. Thermoregulation becomes increasingly important as scorpions expand their territorial ranges into environments with greater temperature variation than aquatic habitats provide. Behavioral adaptations develop to exploit environmental temperature patterns for maintaining optimal body temperatures, while physiological modifications enhance tolerance for temperature fluctuations that exceed those encountered in aquatic environments. Water balance represents one of the most significant physiological challenges facing scorpions making the transition to terrestrial life. Specialized water conservation mechanisms evolve to minimize losses through respiratory surfaces while maintaining adequate hydration for cellular processes. Behavioral adaptations include seeking high-humidity microenvironments and timing activity patterns to coincide with periods of reduced evaporative stress. Prey detection in terrestrial environments requires sensory adaptations that exploit the different physical properties of aerial versus aquatic media. Vibrational detection systems develop enhanced sensitivity to substrate-transmitted signals, while chemical detection capabilities adapt to process airborne rather than waterborne chemical information about prey locations and movement patterns. The metamorphosis from aquatic to terrestrial lifestyle occurs gradually over many generations, with each successive adaptation building upon previous modifications in ways that maintain functional integration while expanding ecological capabilities. Individual scorpions that successfully exploit terrestrial resources gain access to prey communities and territorial opportunities that remain unavailable to their purely aquatic relatives. Ecological interactions with established terrestrial arthropod communities create both competitive pressures and predatory opportunities that shape the evolutionary trajectories of early terrestrial scorpions. Predation on smaller terrestrial arthropods provides nutritional resources that support further terrestrial adaptation, while competition with established terrestrial predators creates selective pressures that favor enhanced hunting efficiency and territorial capability. Social behaviors that functioned in aquatic environments require modification to operate effectively in terrestrial contexts, where different physical and chemical communication mechanisms predominate. Mating behaviors adapt to terrestrial environmental conditions, while aggressive interactions develop modified patterns that account for the different biomechanical constraints of terrestrial versus aquatic combat. As these ancient scorpions continue their patient exploration of terrestrial possibilities, each successful hunt on land, each successful adaptation to aerial environments, contributes to the expansion of arthropod ecological influence into habitats that previously remained beyond arthropod reach. The mudflats that mark the boundary between aquatic heritage and terrestrial future become testing grounds for evolutionary innovations that will reshape the distribution of predatory pressure across Earth's expanding terrestrial ecosystems. The tracks they leave in soft sediments tell stories of exploration and adaptation that fossil preservation occasionally captures for study by scientists working hundreds of millions of years in the unimaginable future. The mayfly's brief Carboniferous summer unfolds in temporal patterns that compress entire life stories into hours of aerial existence. Yet these ephemeral insects emerge from oxygen-rich waters with body sizes and behavioral complexities that dwarf their modern descendants. Ephemeroptera rise from streams and ponds in synchronized emergences that transform aquatic environments into aerial theaters where reproduction, feeding, and death occur within time frames that measure sunset to sunrise rather than seasons to years. Aquatic nymphs spend multiple years developing in the nutrient-rich waters that characterize Carboniferous wetland systems. These underwater juveniles function as efficient predators in their own right, exploiting the abundant oxygen dissolved in ancient water bodies to support metabolic rates that enable rapid growth and active hunting behaviors. Their gill systems extract dissolved gases with efficiency levels that support body sizes substantially larger than those achieved by mayfly nymphs in contemporary aquatic environments. The transformation from aquatic nymph to aerial adult represents one of the most dramatic metamorphoses in the insect world, requiring fundamental reorganization of respiratory, digestive, and reproductive systems within time periods measured in hours rather than days. Tracheal systems replace aquatic gills as oxygen delivery mechanisms, while digestive systems undergo reduction or complete elimination in preparation for adult lifestyles, focused entirely on reproduction rather than feeding. Scientists studying Carboniferous mayfly fossils encounter preservation conditions that occasionally capture both aquatic nymphs and aerial adults in remarkable detail. Fine-grained sediments deposited in quiet water environments preserve delicate gill structures, wing venation patterns, and even traces of soft tissue organization that provide insights into the physiology and behavior of these ancient ephemeral insects. Wing development in giant Carboniferous mayflies requires architectural innovations that scale up the basic flight membrane design to accommodate larger body masses while maintaining the structural integrity necessary for controlled aerial movement. Venation patterns become more complex and robust, while wing membrane thickness increases to provide adequate strength without excessive weight penalties that would compromise flight performance. Only took atmospheric oxygen abundance a few million years to enable mayfly body sizes that exceed modern limits by substantial margins. Only took subsequent atmospheric changes to constrain mayfly dimensions back to the modest sizes that characterize contemporary species. Only took evolutionary time's patient work to create and then eliminate some of the most impressive examples of ephemeral insect life in Earth's history. The synchronization mechanisms that coordinate mass emergences involve chemical communication systems that operate across entire watershed areas. Pheromone compounds released by early emerging individuals trigger coordinated emergence responses in neighboring populations, creating swarm events that can involve millions of individuals rising from aquatic environments within periods of hours or days. Mating behaviors occur in aerial swarms that create three-dimensional mating aggregations extending hundreds of meters above water surfaces. Males engage in complex flight displays that demonstrate fitness to potential mates while competing for access to reproductive females. The temporal constraints imposed by extremely short adult lifespans create intense selective pressure for efficient mate location and courtship behaviors. The reproductive physiology of adult mayflies operates under extreme time pressure, with entire reproductive cycles compressed into time frames that require maximum efficiency in gamete production, mate location, and offspring dispersal. Energy reserves accumulated during aquatic juvenile stages must sustain all adult activities, including flight, courtship, mating, and egg-laying, without additional nutritional input from feeding. Egg deposition strategies evolve to maximize offspring survival while accommodating the brief temporal window available for reproductive activities. Females develop enhanced egg-carrying capacity and precision egg placement behaviors that optimize developmental success for offspring that will spend years developing in aquatic environments before experiencing their own brief aerial reproductive phases. Predation pressure on adult mayflies comes primarily from aerial predators, including early flying reptiles, large dragonflies, and other flying insects capable of capturing prey during flight. The brief temporal window of adult vulnerability creates intense selective pressure for flight speed, maneuverability, and anti-predator behaviors that maximize survival during the critical reproductive period. Chemical communication during mating swarms involves complex pheromone systems that enable species recognition, mate quality assessment, and reproductive synchronization across large populations. These chemical signals must operate effectively in the humid atmospheric conditions that characterize Carboniferous environments while maintaining specificity necessary to prevent hybridization between closely related species. The energetics of mayfly reproduction require careful allocation of limited energy reserves between flight activity, reproductive behavior, and egg production. Females face particularly intense energy constraints due to the substantial investment required for egg development, while males must balance energy allocation between sustained flight activity and competitive courtship displays. Flight mechanics in large Carboniferous mayflies exploit atmospheric conditions that provide enhanced lift generation and reduced energetic costs for sustained aerial activity. Wing beat frequencies adapt to accommodate larger body masses while maintaining the flight speeds necessary for effective predator avoidance and mate location during competitive mating swarms. Environmental timing cues that trigger emergence events include water temperature patterns, photoperiod changes, and chemical signals that indicate optimal environmental conditions for aerial reproductive activities. These cues must integrate information about local environmental conditions with population-level synchronization requirements to optimize emergence timing across entire watershed systems. Dispersal capabilities of adult mayflies enable gene flow between distant aquatic habitats while accommodating the brief temporal constraints of adult aerial phases. Flight range limitations require strategic habitat selection by egg-laying females to ensure access to suitable aquatic development sites for offspring that will spend years in underwater environments. The ecological impact of mass mayfly emergences extends throughout both aquatic and terrestrial food webs, providing massive but temporally concentrated nutritional inputs for predator communities while temporarily reducing aquatic predation pressure on other invertebrate populations. These emergence events represent some of the most dramatic examples of temporal resource concentration in Carboniferous ecosystems. Fossilization of mayfly remains occurs primarily when mass emergence events coincide with environmental conditions that promote rapid burial and preservation. Volcanic ash deposits, flood events, and rapid sediment deposition create preservation scenarios that capture snapshots of these ephemeral populations in remarkable detail. Weather sensitivity in adult mayflies requires behavioral adaptations that accommodate atmospheric conditions during brief aerial phases. Wind patterns, humidity levels, and temperature fluctuations all influence flight performance and reproductive success during the critical hours that comprise entire adult lifespans. As mayfly swarms rise from oxygen-rich waters into atmospheric abundance that will never again support such impressive ephemeral giants. Their brief aerial existence embodies the temporal paradoxes that characterize life in deep time. Hours of individual existence become preserved in fossil records that span hundreds of millions of years, while reproductive behaviors that last minutes create genetic lineages that persist across geological eras. The swarms disperse as quickly as they formed, leaving behind fertilized eggs that will develop in aquatic environments for years before emerging into atmospheric conditions that may no longer support the giant sizes achieved by their parents. Each emergence represents both an ending and a beginning, a brief intersection of atmospheric chemistry and evolutionary possibility that captures the ephemeral nature of all biological existence. Amber's first captured moments begin with tree resins that flow like liquid time across bark surfaces damaged by wind, weather, and the feeding activities of countless small arthropods. These early coniferous trees produce defensive secretions that trap small insects with the patience of geological preservation, creating time capsules that will hold delicate wing scales, compound eye structures, and intricate arthropod anatomical details for hundreds of millions of years. The chemistry of resin production involves complex organic compounds that remain stable under burial conditions, gradually transforming from sticky tree secretions into fossilized amber through polymerization processes that occur over millions of years. These chemical transformations preserve organic structures with fidelity that exceeds most other fossilization processes, capturing cellular details that provide unprecedented insights into Carboniferous arthropod anatomy. Trapped insects within Carboniferous amber represent predominantly small species that became entangled in fresh resin flows while engaging in feeding, mating, or territorial behaviors on tree surfaces. The preservation process captures individuals in moments of active behavior, providing behavioral insights that complement the anatomical information available from more conventional fossil preservation. Scientists studying amber inclusions encounter preservation conditions that maintain original coloration patterns, internal organ structures, and even traces of muscle tissue organization. These exceptional specimens provide reference standards for understanding arthropod physiology during the period when atmospheric conditions supported the largest terrestrial arthropods in Earth's history. The resin-producing trees that create these preservation opportunities represent early experiments in coniferous evolution, developing chemical defense systems that protect against herbivorous insects while inadvertently creating some of the most detailed fossil records available for Carboniferous arthropod communities. The defensive compounds that comprise tree resins evolved to deter feeding damage while maintaining the flow properties necessary for effective wound sealing. Only took resin chemistry millions of years to develop the chemical stability necessary for long-term preservation. Only took burial processes additional millions of years to transform organic secretions into fossilized amber. Only took the intersection of biological behavior and chemical preservation to create time capsules that capture arthropod details invisible in other fossil types. The entrapment process typically involves multiple stages of resin flow that create complex three-dimensional preservation scenarios. Initial resin contact immobilizes struggling insects, while subsequent resin flows encapsulate trapped specimens completely, excluding oxygen and creating anaerobic conditions that prevent bacterial decomposition of organic tissues. Microscopic examination of amber inclusions reveals preservation of structures as delicate as wing membrane venation, sensory hair arrangements, and compound eye facet organization. These details provide insights into sensory capabilities, flight mechanics, and behavioral adaptations that cannot be inferred from conventional fossil specimens that preserve only hard exoskeleton structures. Behavioral preservation in amber captures insects engaged in activities that provide direct evidence of Carboniferous arthropod behavior patterns, mating pairs, feeding behaviors, and social interactions appear in amber specimens with clarity that transforms abstract fossil forms into dynamic components of ancient ecosystems operating according to behavioral principles, recognizable in modern arthropod communities. The taxonomic diversity preserved in Carboniferous amber includes representatives of insect groups that survive to the present, alongside extinct lineages that provide insights into evolutionary pathways not represented in contemporary fauna. These amber biotas serve as reference communities for understanding ecosystem structure during the period of maximum arthropod size diversity. Chemical analysis of amber matrix materials provides environmental information about ancient forest communities, including plant biochemistry, atmospheric composition, and even traces of ancient microorganisms that shared resin environments with trapped arthropods. This chemical information complements morphological data to create comprehensive pictures of ancient ecological relationships. The distribution of amber deposits across Carboniferous geological formations reflects the geographic extent of resin-producing forest communities and the environmental conditions necessary for amber preservation. Successful amber formation requires specific burial conditions that protect organic materials from oxidation, while providing the pressure and temperature conditions necessary for resin polymerization. Preservation bias in amber assemblages favors small arthropods capable of becoming trapped in resin flows, creating fossil communities that emphasize the smaller components of Carboniferous arthropod diversity. These preserved communities complement other fossil types that better represent larger arthropod species, providing comprehensive views of ancient size distributions and ecological relationships. Comparative studies of Carboniferous amber biotas with younger amber assemblages reveal evolutionary trends in arthropod diversity, morphology, and ecological specialization across geological time. These comparisons provide insights into the long-term consequences of atmospheric changes that ended the period of arthropod gigantism. The optical properties of amber permit detailed study of internal arthropod structures using non-destructive imaging techniques that reveal soft tissue organization, internal organ systems, and developmental features that remain invisible in compressed fossil specimens. These techniques enable comprehensive anatomical studies without damaging irreplaceable specimens. Developmental stages preserved in amber include juvenile insects that provide insights into growth patterns, molting processes, and life cycle characteristics of Carboniferous arthropod communities. These developmental specimens bridge the gap between adult morphology and ecological function by revealing the intermediate stages that connect hatching to reproductive maturity. Ecological interactions preserved in amber include predator-prey relationships, parasitic associations, and commensal relationships that operated within Carboniferous forest communities. These behavioral fossils provide direct evidence of food web structure and ecological dynamics that must otherwise be inferred from indirect evidence in conventional fossil assemblages. Seasonal preservation patterns in amber deposits reflect the temporal dynamics of resin production and arthropod activity cycles in ancient forest ecosystems. These patterns provide insights into Carboniferous seasonality, reproductive timing, and environmental rhythms that influenced ecosystem function during the period of maximum arthropod diversity. Anatomical details preserved in amber specimens include structures as delicate as reproductive organs, digestive tract organization, and nervous system components that provide physiological insights into how large Carboniferous arthropods manage basic biological functions. These details inform understanding of the metabolic and physiological innovations that enabled arthropod gigantism. The preservation process occasionally captures arthropods in association with plant materials, pollen grains, and other organic debris that provide ecological context for understanding habitat preferences and feeding relationships in Carboniferous forest communities. These associations reveal ecological specializations that shaped arthropod evolution during this critical period. As tree resins continue their patient work of preservation, capturing moments of ancient life in crystalline tombs that will outlast the mountains around them. Each trapped specimen becomes a messenger from an era when Earth's atmospheric chemistry permitted biological experiments that will never be repeated. The amber holds these messengers in perfect suspension, their compound eyes still gleaming with reflected light, their wings still spread as if frozen mid-flight through air that carried twice the oxygen of modern atmospheres. The resin flows onward, carrying its cargo of captured time toward burial conditions that will transform sticky tree secretions into windows through which future scientists will glimpse the intimate details of life during Earth's most ambitious experiment in arthropod size and diversity. The gradual thinning of air begins with processes so subtle that no individual organism experiences the change as catastrophic transformation. Atmospheric oxygen concentrations decline from their Carboniferous peaks through mechanisms that operate across millions of years, reducing the gaseous abundance that temporarily suspended normal arthropod size constraints. Carbon burial rates slow as bacterial evolution develops enzymatic pathways capable of efficient lignin decomposition, returning previously sequestered carbon to atmospheric circulation as carbon dioxide. The atmospheric chemistry that enabled arthropod gigantism shifts incrementally toward compositions that will characterize later geological periods. Each percentage point decrease in oxygen concentration creates metabolic constraints that slightly favor smaller body sizes, more efficient respiratory systems, and behavioral adaptations that reduce energy expenditure. The changes accumulate across generations like interest compounding in reverse, gradually foreclosing biological possibilities that seemed permanent during their brief geological moment. Plant communities adapt to changing atmospheric conditions through evolutionary modifications that affect carbon cycling, oxygen production, and ecosystem structure. The widespread swamp forests that dominated Carboniferous landscapes fragment as climate patterns shift and drainage conditions change. Tree communities develop enhanced lignin decomposition resistance mechanisms, while bacterial communities evolve counter-adaptations that restore efficiency to organic matter breakdown. Scientists studying the atmospheric transition encounter evidence preserved in geological formations that span the critical period when oxygen concentrations began their long decline toward modern levels. Carbon isotope ratios in marine sediments, plant fossil assemblages, and geochemical signatures in ancient soils provide quantitative evidence for the atmospheric changes that ended arthropod gigantism. The metabolic implications of declining oxygen availability create selection pressures that favor arthropods with more efficient respiratory systems, enhanced oxygen delivery mechanisms, and body sizes that optimize surface area to volume ratios for gas exchange. These evolutionary responses occur gradually across multiple generations, with each successive population adapting to slightly more challenging atmospheric conditions. Only took bacterial innovation several million years to develop lignin decomposition capabilities that restored carbon cycle efficiency. Only took atmospheric responses additional millions of years to reduce oxygen concentrations toward pre-Carboniferous levels. Only took evolutionary times patient work to close the atmospheric window that temporarily permitted arthropod body sizes that defied normal physiological constraints. Respiratory physiology in declining oxygen environments requires architectural modifications that improve gas exchange efficiency while accommodating the constraints imposed by arthropod body plans. Tracheal systems develop enhanced branching patterns that penetrate deeper into body tissues, while spiracle control mechanisms evolve greater precision in regulating airflow to match metabolic demands with atmospheric supply. Behavioral adaptations to reduced oxygen availability include modifications in activity patterns, territorial strategies, and energy allocation decisions that optimize survival in atmospheric conditions that no longer support maximum metabolic rates. Flight behaviors become more energy efficient, while terrestrial locomotion adapts to minimize oxygen consumption during periods of peak activity. Competitive interactions intensify as atmospheric conditions that once supported large arthropod populations begin constraining population sizes and territorial ranges. Species that previously coexisted through habitat partitioning face increased competition for limited resources as environmental carrying capacity decreases in response to atmospheric changes. Reproductive strategies adapt to atmospheric constraints through modifications that optimize offspring survival in environments where larger body sizes become increasingly disadvantageous. Egg production shifts toward smaller, more numerous offspring that require less metabolic investment per individual while maintaining population reproductive potential under changing atmospheric conditions. The ecological cascades triggered by declining atmospheric oxygen extend throughout terrestrial ecosystems as arthropod communities undergo size reductions that affect predator-prey relationships. Pollination networks and decomposer community structure. Predators that specialized in hunting large arthropod prey must adapt to smaller prey items or face extinction as their preferred food sources disappear. Forest ecosystem structure changes as the largest arthropod herbivores and decomposers decline in abundance and size. Plant communities experience reduced herbivory pressure from giant arthropods while facing modified decomposition rates, as smaller arthropod communities process organic matter with different efficiency patterns than their giant predecessors. Biomechanical constraints reassert their influence as atmospheric conditions return toward levels where the relationship between oxygen delivery and metabolic demand creates insurmountable barriers to large arthropod body sizes. The temporary suspension of these physical laws ends as gradually as it began, restoring normal relationships between atmospheric chemistry and biological possibility. Fossil assemblages from the transitional period preserve evidence of the gradual size reduction that characterizes arthropod evolution during atmospheric oxygen decline. Successive geological layers show decreasing maximum sizes for arthropod species, documenting the real-time evolutionary responses to changing atmospheric chemistry across multiple lineages simultaneously. Physiological stress responses develop in arthropod populations experiencing the early stages of atmospheric oxygen decline, Enhanced oxygen extraction efficiency, modified hemolymph chemistry, and improved circulation patterns represent evolutionary adaptations that postpone the size reductions that ultimately become inevitable as atmospheric conditions continue changing. Migration patterns shift as atmospheric conditions become spatially variable across geographic regions. Arthropod populations track optimal atmospheric conditions across landscapes, creating dynamic distribution patterns that respond to both seasonal variation and long-term atmospheric trends toward reduced oxygen availability. Evolutionary innovations during the transition period include respiratory system modifications that will persist long after atmospheric conditions stabilize at lower oxygen concentrations. These adaptations represent permanent improvements in arthropod respiratory efficiency that enable survival in atmospheric conditions that would have been challenging for their Carboniferous ancestors. The extinction patterns that emerge during atmospheric transition show taxonomic selectivity that favors lineages with respiratory and metabolic characteristics that remain functional under reduced oxygen conditions. Giant arthropod species with minimal respiratory efficiency adaptations face higher extinction risks than smaller species or those with enhanced gas exchange capabilities. Preservation conditions during the transitional period create fossil assemblages that document the temporal dynamics of arthropod size reduction in remarkable detail. These fossil sequences provide quantitative evidence for the relationship between atmospheric chemistry and maximum arthropod body size across multiple independent evolutionary lineages. Climate feedback mechanisms accelerate atmospheric changes as reduced carbon burial rates allow previously sequestered carbon to return to atmospheric circulation. These positive feedback loops create accelerating rates of atmospheric change that outpace evolutionary adaptation rates for the largest arthropod species. Microenvironmental refugia develop in locations where local conditions maintain oxygen concentrations that approach Carboniferous levels. These refugia support relic populations of large arthropods that persist briefly after atmospheric conditions in surrounding areas become unsuitable for giant body sizes. The biogeochemical cycles that govern atmospheric oxygen production and consumption achieve new equilibrium states that will characterize Earth's atmospheric chemistry for hundreds of millions of years. These new equilibria establish the atmospheric constraints that will govern arthropod evolution throughout subsequent geological periods. Adaptive radiation occurs among smaller arthropod lineages as ecological niches previously occupied by giants become available for colonization by species with body sizes appropriate for post-Carboniferous atmospheric conditions. These radiations create the taxonomic diversity patterns that will characterize arthropod communities throughout later geological periods. As atmospheric oxygen concentrations continue their gradual decline toward levels that will constrain arthropod body size for the remainder of Earth's history. Each percentage point reduction closes additional chapters in the story of biological possibility that briefly flourished under temporarily enhanced atmospheric conditions. The giants grow smaller with each generation, their reduced offspring inheriting a world where the very air that once supported ambitious scale now demands modest dimensions and efficient physiology. The atmospheric abundance that seemed permanent during its geological moment reveals itself as temporary as weather. As ephemeral as the individual lives of the organisms it briefly permitted to grow beyond normal limits. The air thins with geological patience, restoring constraints that will govern biological architecture until the sun itself grows old and changes the rules of planetary chemistry through stellar rather than biological evolution. Ice Age interruptions to the green begin as subtle shifts in global climate patterns that gradually fragment the vast tropical forests that supported oversized insect ecosystems across continental landscapes. The first glacial episodes develop at high latitudes, where accumulating ice sheets lock away ocean water and create feedback loops that amplify cooling trends across the planet. These climate oscillations introduce temporal variability to environmental conditions that previously remained stable for millions of years. The continental ice sheets that characterize these early glacial periods advance and retreat with cyclical regularity that disrupts the stable wetland conditions necessary for maintaining the carbon burial processes that characterize peak Carboniferous environments. Forest communities that once extended unbroken across vast geographic areas become fragmented into isolated refugia, separated by expanding grasslands and seasonal wetlands that cannot support the largest arthropod species. Atmospheric circulation patterns shift as temperature gradients between ice-covered polar regions and ice-free equatorial areas create enhanced weather system intensity and seasonal variation. The stable, humid conditions that favored continuous forest growth give way to more variable climate patterns that create periodic droughts, temperature fluctuations, and seasonal extremes that challenge organisms adapted to consistent environmental conditions. Scientists studying the transition from greenhouse to icehouse climate conditions encounter geological evidence that documents the environmental changes that contributed to ending arthropod gigantism. Glacial deposits, changing plant fossil assemblages, and sedimentological evidence for climate variability provide quantitative data about environmental conditions during this critical transition period. Plant community composition changes dramatically as climate variability selects against tree species adapted to stable wetland conditions while favoring species capable of surviving periodic droughts and temperature fluctuations. The tree ferns and early conifers that dominated Carboniferous forests decline in abundance and geographic distribution, replaced by plant communities better adapted to variable environmental conditions. Only took glacial-interglacial cycles several million years to establish patterns of climate variability that persisted throughout subsequent geological periods. Only took these climate oscillations additional time to fragment forest ecosystems that had supported arthropod gigantism for tens of millions of years. Only took the patient work of astronomical cycles to introduce environmental variability that ended Earth's most stable period of terrestrial ecosystem development. Hydrological changes accompanying glacial cycles create drainage patterns that eliminate many of the extensive wetland systems that supported carbon burial and atmospheric oxygen enrichment during peak Carboniferous conditions. River systems develop enhanced gradients and flow variability that create more dynamic aquatic environments while reducing the area available for peat formation and organic matter accumulation. Seasonal temperature variation increases dramatically as polar ice sheets create enhanced temperature gradients that drive more intense weather systems across previously temperate continental areas. Arthropod species adapted to stable temperature conditions face physiological challenges that require enhanced thermoregulation capabilities or behavioral adaptations that accommodate greater temperature range. Forest fragmentation creates isolated habitat patches that cannot support the territorial ranges required by the largest arthropod species: giant millipedes, massive spiders, and enormous flying insects find their habitat requirements incompatible with the reduced patch sizes that result from climate-driven ecosystem fragmentation across continental landscapes. Migration corridors that previously connected distant forest areas become interrupted by expanding grasslands and seasonal wetlands that create barriers to arthropod dispersal. Species that require continuous forest canopy for movement between feeding and breeding areas face population isolation that reduces genetic diversity and adaptive potential. Competitive interactions intensify within fragmented habitat patches, as arthropod species with large territorial requirements find themselves confined to smaller areas with reduced resource availability. The ecological carrying capacity of isolated forest fragments cannot support the population densities that characterized continuous forest ecosystems during peak Carboniferous conditions. Predator-prey relationships shift, as habitat fragmentation creates edge effects that modify community structure within remaining forest patches. Increased exposure to environmental variability along habitat edges creates additional stress on arthropod populations while providing access corridors for species adapted to more open environmental conditions. Reproductive success decreases for arthropod species that require large territories for successful mating and offspring dispersal. Habitat fragmentation reduces the probability of successful mate location, while increasing the risks associated with dispersal movements between isolated habitat patches. Food web stability declines as ecosystem fragmentation reduces the population sizes and species diversity that provide resilience against environmental perturbations. Simplified food webs and fragmented habitats become more vulnerable to cascading effects that can eliminate key species and destabilize entire ecological communities. Microclimate conditions within forest fragments differ significantly from those in continuous forest systems, creating environmental challenges that require physiological and behavioral adaptations by arthropod species adapted to stable forest interior conditions. Edge effects penetrate deeply into small habitat patches, reducing the area available for species requiring forest interior conditions. Extinction debt accumulates in fragmented populations as reduced population sizes and genetic diversity create delayed extinction risks that manifest over multiple generations following initial habitat fragmentation. Species that initially survive habitat reduction face long-term extinction risks due to demographic and genetic factors associated with small population size. Evolutionary responses to habitat fragmentation include behavioral modifications that enhance dispersal capability and physiological adaptations that improve tolerance for environmental variability. These adaptations represent evolutionary adjustments to environmental conditions that differ dramatically from those that selected for arthropod gigantism during stable Carboniferous conditions. Refugial populations persist in geographic areas where local environmental conditions maintain forest ecosystem structure despite regional climate changes. These refugia provide source populations for recolonization of suitable habitat during interglacial periods when forest ecosystems temporarily expand their geographic distribution. Glacial interglacial cycles create repeated episodes of habitat expansion and contraction that prevent the establishment of stable evolutionary equilibria in arthropod communities. This environmental instability favors species with enhanced dispersal capabilities and broad environmental tolerance rather than specialized adaptations to particular habitat conditions. Biogeographic patterns that develop during repeated glacial cycles create geographic distributions that persist long after the specific climate conditions that created them have changed. These historical biogeographic effects influence contemporary arthropod distribution patterns and evolutionary trajectories in ways that reflect ancient climate oscillations. As ice sheets advance and retreat with astronomical regularity, each glacial cycle removes another piece of the environmental stability that once supported arthropod giants across continental landscapes. The green retreats toward equatorial refugia, carrying with it the diminished descendants of organisms that once grew large under atmospheric abundance and climatic stability that will never again coincide in Earth's future. The forests fragment and reunite and fragment again, writing stories of environmental change and the geographic distributions of species that grow smaller with each cycle. Their reduced descendants adapting to a world where stability becomes memory, and variability becomes the only constant in terrestrial ecosystem dynamics. The Permian's approaching threshold manifests in geological processes that operate beneath the surface awareness of the arthropod communities, still clinging to their diminished versions of Carboniferous gigantism. Continental drift accelerates the assembly of Pangea, bringing landmasses together in configurations that will create the largest continental landmass in Earth's history, while fundamentally altering ocean circulation patterns and atmospheric dynamics across the planet. Volcanic activity increases dramatically as tectonic processes associated with continental collision create magmatic provinces that will eventually produce the most extensive volcanic eruptions in Earth's history. The Siberian traps begin their formation processes, setting the stage for volcanic outgassing that will transform atmospheric chemistry and create environmental conditions hostile to most forms of complex life. Ocean circulation patterns undergo fundamental reorganization, as the configuration of continental landmasses eliminates many of the oceanic basins that previously moderated global climate patterns. The vast Panthalassa Ocean dominates the planet's hydrosphere, creating oceanic circulation patterns that concentrate climatic extremes rather than moderating them through geographic heat distribution. Scientists studying the transition from Carboniferous to Permian environmental conditions encounter evidence of accelerating environmental change preserved in geological formations that span this critical period. Volcanic ash layers, changing marine chemistry, and shifting terrestrial ecosystem composition provide quantitative evidence for the environmental deterioration that preceded the most severe mass extinction in Earth's history. Atmospheric chemistry shifts towards compositions that become increasingly hostile to terrestrial life as volcanic outgassing introduces toxic compounds while simultaneously altering the oxygen and carbon dioxide concentrations that govern arthropod physiology. Sulfur dioxide emissions from increased volcanic activity create acid precipitation that damages plant communities and acidifies terrestrial and aquatic environments. Only took continental assembly several million years to create geographic configurations that destabilized global climate systems. Only took volcanic processes additional time to create atmospheric conditions that eliminated most complex terrestrial life. Only took the convergence of geological processes to end not only arthropod gigantism, but most of the evolutionary experiments that characterized Paleozoic terrestrial ecosystems. Climate patterns become increasingly extreme as the vast continental interior of Pangaea develops arid conditions that extend across thousands of kilometers. Seasonal temperature variation increases dramatically as continental climate patterns replace the oceanic moderation that characterized smaller, more dispersed continents during earlier geological periods. Desert expansion accelerates across continental interiors as changing precipitation patterns create vast arid regions that eliminate most of the forest ecosystems that supported diverse arthropod communities. The humid to stable conditions that favored arthropod diversity give way to extreme environmental conditions that select for only the most environmentally tolerant species. Marine ecosystem collapse begins as changing ocean chemistry creates anoxic conditions that eliminate most marine life forms. The oceanic food webs that supported terrestrial ecosystems through nutrient cycling and climate moderation become simplified to the point where they can no longer maintain the productivity that sustained complex terrestrial communities. Soil chemistry changes as acid precipitation and changing plant communities alter the biogeochemical processes that maintain soil fertility. The organic-rich soils that supported diverse plant communities during the Carboniferous become depleted and acidified, creating growing conditions that support only a limited range of plant species adapted to harsh chemical environments. Plant extinction cascades eliminate many of the tree species that provided habitat structure for arthropod communities, while simultaneously removing the primary productivity that supported terrestrial food webs. Forest ecosystems collapse across vast geographic areas, replaced by simplified plant communities dominated by species capable of surviving extreme environmental conditions. Food web simplification accelerates as the environmental stresses that affect primary producers cascade through terrestrial ecosystems to eliminate most specialized arthropod species. The complex ecological relationships that supported arthropod diversity during stable Carboniferous conditions become impossible to maintain under increasingly harsh environmental conditions. Physiological stress increases beyond tolerable limits for most arthropod species, as multiple environmental factors combine to create challenges that exceed adaptive capacity. Temperature extremes, chemical pollution, habitat loss, and food web collapse create synergistic effects that overwhelm the evolutionary adaptations that previously enabled arthropod success. Extinction rates accelerate exponentially as environmental deterioration outpaces evolutionary adaptation across multiple arthropod lineages simultaneously. Species that survived previous environmental challenges find themselves facing combinations of stresses that exceed their adaptive capabilities despite millions of years of evolutionary refinement. Genetic diversity declines rapidly in arthropod populations as habitat fragmentation and population reduction eliminate most of the evolutionary potential that enabled adaptation to previous environmental challenges. Small isolated populations lose the genetic variation necessary to respond to rapidly changing environmental conditions through evolutionary adaptation. Reproductive failure becomes widespread as environmental stresses disrupt the complex life cycles that characterize most arthropod species. The temporal precision required for successful reproduction becomes impossible to maintain under rapidly changing environmental conditions that eliminate the predictable seasonal patterns necessary for coordinating mating and development. Behavioral adaptations that previously enabled arthropod survival under challenging conditions become ineffective as environmental changes exceed the range of variation for which existing behavioral repertoires provide adequate responses. Migration patterns, feeding strategies, and reproductive behaviors fail to function under unprecedented environmental conditions. Ecosystem services provided by arthropod communities collapse as diversity and abundance decline below threshold levels necessary to maintain pollination. Decomposition and predation processes that support terrestrial ecosystem function. The ecological roles that arthropods played in maintaining ecosystem stability become unfilled as species extinctions eliminate functional groups. Evolutionary dead ends accumulate as lineages that invested heavily in specializations adapted to Carboniferous conditions find themselves unable to adapt quickly enough to survive rapidly changing Permian environmental conditions. Evolutionary strategies that previously provided competitive advantages become liabilities under the new environmental regime. Refuge habitats become increasingly rare as environmental deterioration affects even the most protected geographic locations. The microenvironmental refugia that enabled species survival during previous environmental challenges become insufficient to buffer against the severity and geographic extent of Permian environmental changes. Cascading extinctions accelerate as the loss of key species creates secondary extinction risks for species that depended on extinct species for food. Habitat structure, or other essential ecological services. Food web collapse spreads from primary producers through multiple trophic levels to eliminate entire ecological communities. As continental drift and volcanic processes continue their inexorable work of environmental transformation. The arthropod giants that briefly flourished under atmospheric abundance and climatic stability face their final challenge. The approaching threshold represents not just another environmental change requiring adaptation, but a fundamental reorganization of terrestrial environmental conditions that will eliminate most complex life forms and reset evolutionary trajectories for the survivors. The threshold approaches with geological inevitability, carrying with it the end of an era when Earth's surface environments permitted biological experiments in scale and diversity that will never be repeated under the environmental constraints that will characterize subsequent geological periods. Fossils in future stone begin their formation in the quiet moments when giant arthropods complete their final activities and settle into sediments that will preserve their forms for hundreds of millions of years. The delicate process of fossilization captures these magnificent creatures at the moment when atmospheric abundance can no longer sustain their impressive dimensions, creating permanent records of biological experiments that temporarily defied the normal constraints governing arthropod architecture. Fine-grained sediments accumulate around the bodies of deceased giant dragonflies. Their wings spread in final flight positions that will become impressed into rock layers with startling fidelity. The exceptional preservation conditions that characterize some Carboniferous deposits maintain details of wing venation, compound eye structure, and even traces of soft tissue organization that provide unprecedented insights into the anatomy of these ancient aerial giants. Compression fossils form as the weight of accumulating sediments gradually flattens arthropod exoskeletons, while chemical processes replace organic materials with mineral replicas that maintain original shapes and surface textures. The transformation from living tissue to stone occurs through molecular replacement processes that preserve biological architecture in permanent mineral form. Scientists working hundreds of millions of years in the future will extract these fossil treasures from rock formations that span continents, using techniques and technologies that the arthropods themselves could never imagine. Careful excavation reveals complete specimens that tell stories of ancient ecology, atmospheric chemistry, and evolutionary experimentation during Earth's brief period of arthropod gigantism. The preservation process itself becomes a form of geological time travel, capturing moments of ancient life in crystalline matrices that survive mountain building, continental drift, and climate changes that reshape Earth's surface multiple times over. Each fossil represents a message transmitted across deep time from an era when different physical laws governed biological possibility. Only took sedimentary processes millions of years to transform organic remains into mineralized replicas that preserve anatomical details with startling accuracy. Only took geological time additional millions of years to bury these treasures beneath rock layers that protect them from surface weathering until future discovery. Only took the patient work of Earth's archive keeping to preserve evidence of biological experiments that lasted mere millions of years, yet remain accessible across hundreds of millions. Chemical fossilization follows pathways that replace calcium carbonate exoskeletons with more stable mineral forms including silica, pyrite, and various carbonate minerals that maintain structural integrity across geological timescales. These chemical substitutions occur gradually through groundwater processes that introduce replacement minerals while removing original biological materials. Trace fossils preserve evidence of arthropod behavior, including walking tracks, burrow systems, and feeding traces that provide insights into daily activities and ecological relationships that cannot be inferred from body fossils alone. These behavioral fossils capture the dynamic aspects of ancient arthropod life that complement the anatomical information available from preserved body parts. Exceptional preservation sites develop under specific environmental conditions that exclude oxygen, prevent bacterial decomposition, and facilitate rapid burial under fine sediments. These geological jackpots preserve arthropod fossils with completeness and detail that transforms paleontological understanding of ancient ecological relationships and evolutionary processes. Fossil assemblages capture entire communities of interacting arthropod species, preserving evidence of predator-prey relationships, competitive interactions, and ecological specializations that operated within Carboniferous terrestrial ecosystems. These community-level fossils provide insights into ecosystem structure and function during the peak period of arthropod diversity and size experimentation. Microscopic preservation reveals cellular details including muscle fiber organization, nervous system structure, and reproductive organ anatomy that inform understanding of how giant arthropods managed basic physiological functions. These subcellular fossils provide direct evidence for the anatomical innovations that enabled arthropod gigantism under enhanced atmospheric oxygen conditions. Comparative paleontology uses Carboniferous arthropod fossils as reference standards for understanding evolutionary trends in arthropod body size, respiratory system architecture, and ecological specialization across geological time. These ancient giants serve as evolutionary benchmarks that document the maximum achievements possible under temporarily enhanced atmospheric conditions. Stratigraphic relationships between arthropod fossil assemblages and geological formations that preserve evidence of atmospheric chemistry provide quantitative data about the relationship between environmental conditions and maximum arthropod body size. These correlations establish scientific foundations for understanding the environmental controls on arthropod evolution. Taphonomic studies investigate the processes that control arthropod fossil preservation, revealing bias patterns that influence which species and body parts appear in fossil assemblages. Understanding preservation bias enables more accurate reconstruction of ancient arthropod communities and ecological relationships from incomplete fossil evidence. Paleoecological reconstruction using arthropod fossil assemblages creates detailed pictures of ancient ecosystem structure, energy flow patterns, and species interactions that characterize terrestrial communities during the period of maximum arthropod diversity. These reconstructions provide historical baselines for understanding long-term ecological change. Evolutionary developmental studies compare Carboniferous giant arthropod anatomy with modern relatives to identify the developmental modifications that enabled large body size while maintaining functional integration of complex physiological systems. These comparisons reveal evolutionary mechanisms that temporarily overcame normal size constraints. Biomechanical analysis of fossilized arthropod structures provides insights into locomotion, feeding, and flight capabilities that characterize giant ancient species. Engineering principles applied to fossil anatomy reveal performance capabilities that exceeded those of any contemporary arthropod species. Geochemical analysis of fossil-bearing rock formations provides environmental context for understanding the atmospheric and climatic conditions that supported arthropod gigantism. Chemical signatures in sedimentary rocks preserve quantitative evidence about ancient atmospheric oxygen concentrations, temperature patterns, and precipitation regimes. Museum collections preserve the most spectacular arthropod fossils in climate-controlled environments that ensure their availability for future scientific study using techniques and technologies that continue advancing scientific understanding of ancient life. These collections represent irreplaceable scientific resources that document Earth's evolutionary history. Educational programs use giant arthropod fossils to communicate concepts about deep time, evolutionary change, and environmental controls on biological diversity to audiences that span educational levels from elementary school through university research programs. These fossils serve as tangible connections to ancient worlds that stimulate scientific curiosity and environmental awareness. Research technologies continue advancing scientific capabilities for extracting information from arthropod fossils, including CT scanning, electron microscopy, and chemical analysis techniques that reveal previously invisible details about ancient anatomy and physiology. These technological advances ensure that fossil specimens continue providing new scientific insights long after their initial discovery. As sediments continue accumulating around the final generation of giant arthropods, the fossilization process writes permanent records in Earth's geological library. Each preserved specimen becomes a chapter in the story of biological possibility that briefly flourished when atmospheric chemistry permitted evolutionary experiments in scale and complexity. The stone accepts these ancient forms with mineral patience, holding their shapes and stories in crystalline matrices that will outlast continents, survive ice ages, and carry messages across hundreds of millions of years to curious minds that will marvel at evidence of life's brief experiment with arthropod gigantism under atmospheric conditions that Earth will never again provide. The echo of ancient wings resonates through genetic memories that span hundreds of millions of years, carrying forward the evolutionary innovations that once enabled arthropod flight on scales that modern atmospheric conditions cannot support. Contemporary dragonflies execute aerial maneuvers using neural pathways and wing control mechanisms that retain the fundamental architecture developed during Earth's age of atmospheric abundance. Their flight patterns unchanged across the vast expanse of deep time. Modern Libellula and Aishna species demonstrate flight capabilities that represent direct evolutionary inheritance from their Carboniferous ancestors. Though their body sizes remain constrained by contemporary atmospheric oxygen concentrations that limit metabolic support for larger forms. The basic biomechanics of dragonfly flight, the figure-8 wing stroke patterns, the independent control of 4 wings, the precision hovering capabilities, persist unchanged from the era when these same mechanisms powered insects with wingspans that dwarfed modern birds. Neural control systems that coordinate complex flight behaviors in contemporary dragonflies operate through computational architectures that evolved during the Carboniferous period when enhanced atmospheric oxygen supported larger brain volumes and more sophisticated information processing capabilities. These neural networks retain their essential organization despite the size constraints that limit modern dragonfly dimensions to fractions of their ancient relatives. Scientists studying comparative flight mechanics encounter remarkable consistency in dragonfly aerodynamics across geological time, suggesting that natural selection optimized these flight systems during the Carboniferous period, when atmospheric conditions permitted extensive experimentation with different wing designs and control mechanisms. The solutions that evolved during this period remain optimal for arthropod flight under contemporary atmospheric conditions. Compound eye architecture in modern dragonflies preserves the sophisticated visual processing capabilities that enabled their giant ancestors to navigate complex three-dimensional forest environments at high speeds. The ommatidial organization, neural integration pathways, and visual field characteristics that supported hunting behaviors in giant carboniferous dragonflies continue functioning in their smaller contemporary descendants. Only took hundreds of millions of years for atmospheric conditions to constrain dragonfly body size while preserving the essential flight mechanisms that achieved perfection during the brief period of arthropod gigantism. Only took evolutionary conservation to maintain aerodynamic innovations across geological timespans that exceed human comprehension. Only took genetic memory to carry forward the echoes of ancient atmospheric abundance in the wings of insects that will never again achieve such magnificent dimensions. Hunting strategies employed by contemporary dragonflies reflect behavioral patterns that evolved when their ancestors pursued prey items substantially larger than those available in modern ecosystems. The patient territorial behavior, the precision intercept calculations, the explosive acceleration capabilities that characterize modern dragonfly predation represent evolutionary inheritance from ecological relationships that no longer exist. Wing membrane architecture in modern dragonflies maintains the sophisticated venation patterns and structural reinforcement systems that supported much larger wing areas during the Carboniferous period. These design features provide excessive structural strength for contemporary wing sizes, suggesting evolutionary inheritance from ancestors that required enhanced structural integrity for larger flight surfaces. Flight muscle organization in contemporary dragonflies preserves the biochemical pathways and contractile mechanisms that operated at enhanced metabolic rates during atmospheric oxygen abundance. These muscle systems retain capabilities for power output and sustained activity that exceed the requirements for supporting modern dragonfly body sizes, representing biological overcapacity inherited from giant ancestors. Reproductive behaviors in modern dragonflies follow territorial and courtship patterns that evolved when atmospheric conditions supported population densities and individual territory sizes that no longer characterize contemporary ecosystems. Mating flight displays, territorial defense mechanisms, and egg-laying strategies reflect ecological relationships that developed under different environmental constraints. Life cycle timing in contemporary dragonflies maintains synchronization with seasonal patterns and aquatic development phases that originated when their ancestors completed similar life cycles under atmospheric conditions that supported larger aquatic nymphs and more complex predator-prey relationships in freshwater environments. Thermoregulation mechanisms in modern dragonflies include behavioral and physiological adaptations that evolved when atmospheric abundance enabled higher activity levels and more intensive metabolic processes. These thermoregulatory capabilities exceed the requirements for contemporary body sizes, representing evolutionary overdesign inherited from ancestors that generated more metabolic heat. Migration patterns in contemporary dragonfly species follow geographic routes and seasonal timing that originated when atmospheric conditions supported longer flight ranges and more intensive migratory behavior. These migration capabilities represent evolutionary inheritance from ancestors that possessed enhanced flight endurance under atmospheric oxygen abundance. Sensory integration systems in modern dragonflies process environmental information through neural architectures that evolved to coordinate behaviors in ecosystems with greater complexity and diversity than contemporary terrestrial communities provide. These sensory capabilities exceed contemporary ecological requirements, suggesting inheritance from ancestors that operated in more demanding sensory environments. Predator avoidance behaviors in contemporary dragonflies include escape responses and evasive maneuvers that evolved when their ancestors faced predation pressure from aerial predators that no longer exist in modern ecosystems. These anti-predator adaptations represent evolutionary conservation of behavioral solutions to ecological challenges that disappeared millions of years ago. Communication systems in modern dragonflies preserve chemical and visual signaling mechanisms that originated when atmospheric conditions supported population structures and social interactions that exceeded those possible under contemporary environmental constraints. These communication capabilities represent evolutionary inheritance from more complex social ecosystems. Evolutionary developmental pathways in contemporary dragonflies maintain genetic regulatory networks that once controlled the development of larger body sizes and more complex anatomical structures. These developmental programs retain the capability to produce larger forms, but remain constrained by environmental limitations rather than genetic incapacity. Physiological efficiency in modern dragonflies includes respiratory and circulatory enhancements that evolved to support metabolic processes under atmospheric oxygen abundance. These physiological capabilities provide performance margins that exceed contemporary requirements, representing evolutionary preparation for atmospheric conditions that no longer exist. Biomechanical precision in contemporary dragonfly flight reflects engineering optimization that occurred when atmospheric conditions permitted extensive experimentation with aerodynamic design and control system refinement. These biomechanical solutions achieved perfection under conditions that supported larger body sizes while remaining optimal for smaller contemporary forms. Ecological memory embedded in dragonfly behavior patterns preserves evidence of evolutionary relationships and environmental interactions that characterize terrestrial ecosystems during the peak period of arthropod diversity and atmospheric oxygen abundance. These behavioral echoes provide insights into ancient ecological relationships that cannot be reconstructed from fossil evidence alone. As contemporary dragonflies continue their aerial patrols through atmospheres that constrain their ambitions to modest dimensions, each wing beat carries forward the mechanical perfection achieved when Earth's air held twice its current oxygen concentration. Their flight patterns trace invisible lines that connect present skies to ancient atmospheres, genetic memories to geological history, evolutionary inheritance to atmospheric chemistry. The echo continues resonating through every spiral climb, every precision hover, every split-second course correction that demonstrates aerodynamic mastery inherited from ancestors that grew large under atmospheric abundance that Earth provided once and will never provide again. In their wings, the memory of giant times persists, waiting for atmospheric conditions that will never return to support the full expression of evolutionary potential that remains encoded in dragonfly genes. The ancient rhythms slow now, settling into patterns that match the deeper pulses of geological time rather than the quick heartbeats of individual lives. Somewhere beneath layers of sedimentary rock, the fossilized remains of giant dragonflies rest in compressed stillness, their wings spread in permanent flight through stone that was once mud, was once the bottom of shallow seas that dried and filled and dried again across millions of patient years. The atmospheric abundance that briefly permitted such biological audacity has long since dispersed into chemical equilibria that constrain arthropod ambitions to modest scales. Modern insects navigate the same airways through which Meganeura once cast eagle-sized shadows, but they do so on wings measured in centimeters rather than spans that approached human arm reach. The air itself remembers nothing of its former generosity. Deep beneath modern forests, coal seams preserve the compressed remains of the tree ferns and early conifers that forgot how to rot efficiently. Their carbonized bodies forming black layers that will eventually power civilizations that exist hundreds of millions of years beyond the last giant millipedes' methodical journey across forest floors that no longer exist. The carbon that once flowed freely between atmosphere and plant tissue lies locked in geological storage, removing forever the atmospheric chemistry that enabled arthropod gigantism. In laboratories that span the globe, Scientists continue extracting stories from fossilized amber, from compressed wing impressions in shale, from the trace outlines left by creatures whose footprints speak across deep time. Each specimen adds another detail to the picture of life during Earth's brief experiment with biological scale. When the very chemistry of existence operated under different rules. The genetic echoes persist in reduced forms, carrying forward the neural pathways that once coordinated bodies grown large on atmospheric generosity. Modern arachnids construct webs using silk production mechanisms inherited from ancestors that required stronger materials to support the mechanical stresses of larger body masses. Contemporary scorpions hunt using venom delivery systems evolved when prey items measured in meters rather than millimeters. Tidal pools along ancient coastlines where eurypterids once patrolled now host arthropod communities measured by different standards. Their members scurrying through ecological relationships that operate on scales appropriate for atmospheric conditions that will persist until stellar evolution changes the fundamental rules governing Earth's surface chemistry. The silence deepens as the last echoes of Carboniferous ambition fade into the patient acceptance of biological limits restored. No giant wings beat through the humid air. No massive segmented forms traverse elevated pathways through forests that learned, eventually, how to decompose efficiently. No enormous compound eyes track movement across territories that spanned kilometers rather than the modest domains that constrained contemporary arthropod ambitions. In this geological rest, in this return to normal proportions and reasonable expectations, life settles into patterns that will characterize terrestrial ecosystems for hundreds of millions of years. The constraints reassert themselves with the reliability of physical law, creating boundaries that evolution will respect until the sun itself grows old and changes the terms of planetary existence. The deep time settles around these memories like sediment around fossils, preserving the evidence while burying the possibility. Giant times become geological history. Atmospheric abundance becomes fossil chemistry. And the arthropods that briefly defied normal limits become impressions in stone that speak to curious minds across vast expanses of time about the temporary suspension of biological constraints that occurred once, will not occur again, and remains forever captured in the patient archives of Earth's geological memory. Sleep well, ancient giants, sleep well.